There is no space-time under you. You're swimming through it. The more you go down, the weird it gets. Under the smooth cosmic fabric that we think is normal, there is something wild, living, and moving. If you zoom in far enough, not to atoms or quarks, but all the way down to negative 10.35 meters, the surface of reality starts to break apart. It makes foam. It moves around. It has bugs. Empty space is not real down here. Breaks in geometry. Time might not move. And what we think of as real life could just be an image. That being said, what is really under space-time? We should split the world in half to find out. The quantum foam beneath reality. You could imagine getting smaller and smaller until you get so small that even the idea of space starts to break down. The temperature where you are now is between 10 and negative 35 meters. This is the Planck length, which is the largest length that can be measured in the world. And space isn't calm at this depth. It's not smooth anymore. It's very hot. I came up with the word quantum foam to describe this area of the universe. It talks about how space-time is jumbled and foamy at the tiniest sizes you can think of. It's time to forget about the flat grid you learned in school. The quantum level of the universe is more like an angry ocean during a storm, with waves that crash into each other, rise and fall, and disappear faster than a photon can blink. You might ask, how do we even know this foam exists if we can't see it? The answer is, we don't know for sure. But quantum field theory, the framework that underpins most of modern physics, suggests that energy fluctuations in empty space are constantly giving rise to brief, jittery distortions. These fluctuations aren't theoretical window dressing. They have real, measurable effects. The famous Casimir effect, for instance, proves that vacuum energy can exert pressure between two metal plates placed nanometers apart. Something is buzzing in the void, and that something might just be the foam. But what does quantum foam consist of? That's where things get stranger. General relativity and quantum uncertainty start to fight at the Planck scale, which is 10 to 35 meters. From one point of view, quantum physics says that momentum and energy are never really fixed. Objects can appear and disappear. On the other hand, Einstein's equations say that matter and energy can bend space-time. When you mix those two things together, you get a crazy swirl of tiny black holes and wormholes that form and disappear in a matter of seconds. These features, called topological fluctuations, are like bubbles in a cosmic stew. You could imagine a space-time filled with these tiny ghost-like tunnels, miniature wormholes that pop in and out of reality faster than anything we could ever observe. They're not stable structures. They're quantum ghosts. More ideas than objects. More questions than answers. Some physicists think this foam might not just be a byproduct of quantum weirdness. It could be the foundation of everything. According to some quantum gravity theories, this seething microstructure of space-time gives rise to the large-scale universe we know. In other words, what we call space might just be the blurred average of a billion quantum foam bubbles popping beneath our feet every second. This thought also fits with a big question in physics. Why does space-time look smooth at large scales when it's really very chaotic? Picture a computer picture. It looks like a mess of square images up close, but it looks like a smooth picture from far away. In the same way, the quantum foam that is all bubbly might settle down into the smooth space-time we feel at human scales. But if quantum foam is real, why can't we detect it directly? The problem lies in scale and energy. To probe 10 to the minus 35 meters, you'd need a particle accelerator the size of the Milky Way and energies reaching the Planck energy, around 1.2 times 10 to the 19th giga-electron volts. That's roughly 100 trillion times more powerful than what the Large Hadron Collider can produce. We're not just technologically limited, we're fundamentally limited by the structure of space-time itself. There are still side paths to look into. Some researchers want to use gravitational wave monitors, such as LIGO, to look for small jitters in space itself. These could be tiny quantum tremors that could be signs of foam. Others look at strange cosmic events, like high-energy gamma-ray bursts, for signs that light is being delayed or spread by changes in the way reality is put together. And then there's the connection to black holes. Some radical theories suggest that black hole event horizons might be surrounded by quantum foam-like structures, offering a link between spacetime's deepest layers and its most extreme objects. If this is true, then quantum foam might not just be theoretical noise, it might shape how black holes evolve, evaporate, or even connect to other universes. So why does any of this matter? Because being able to understand the quantum foam could be the first step toward bringing quantum mechanics and general relativity together, which is the most important thing in current physics. They both explain everything from atoms to galaxies, but at the Planck scale, they won't work together. Where the known rules break down is in the foam, which is also where a new theory of quantum gravity must come from. There are even ideas that quantum foam might be where time itself began. Time may not have had a clear direction or flow in the early universe, which was mostly made up of foam. It wasn't until the foam settled into a more solid space-time fabric that time started to move forward. That's not just an interest in theory. That's a fresh way to think about why things are the way they are. Virtual particles, the ghosts of empty space. There is nothing around you, not just quiet, but nothing at all. There is no light, heat, air, or atoms. The void isn't still at all, though, if you had quantum eyes. It's living. It is flashing. There are ghostly flashes in the vacuum, which means that particles are coming and going faster than any clock could keep track of. They're called virtual particles, and even though they're not real, they have effects all over the place. This might be the most mind-breaking idea in all of modern physics, that the vacuum, the thing we once assumed was nothing, is actually something. In quantum field theory, every type of particle is associated with a field that stretches across the universe. And these fields never truly shut off, even when you cool them to absolute zero. Quantum uncertainty demands they still jitter. And from that jitter, pairs of virtual particles emerge, one matter, one antimatter, only to annihilate almost instantly. They don't stay around long enough to be found directly. They can't be kept separate or in a bottle. They are real enough to leave their mark on the world, though. The most well-known example is the Casimir effect. If you put two metal plates that are not charged next to each other, nanometers apart in a vacuum, they start to attract each other. There isn't any electric force at work here. Instead, the pressure is coming from the quantum void itself. The particles that are putting that pressure on the plates can't fit through them as easily as they can outside the plates. The plates are pushed together by the unbalance, which shows that the vacuum is full of energy. These particles also help explain how Hawking radiation works. Near a black hole's event horizon, a virtual particle pair might form, but if one falls into the black hole and the other escapes, it becomes a real particle. The black hole loses mass in the process. Over eons, enough virtual particle pairs escaping can cause the black hole to evaporate entirely. So even in the deadest parts of the universe, where gravity crushes light and time, the ghosts of the vacuum are still playing tricks. Virtual particles help mediate forces. When two electrons repel each other, what's actually happening is an exchange of virtual photons, particles that briefly exist during the interaction, transmitting electromagnetic force before vanishing again. In quantum field theory, every force is an interaction involving virtual particle exchange. Even gravity, in theory, would be carried by virtual gravitons if they exist. In this view, what we call forces aren't magical pushes or pulls. They're whispers passed between particles by these invisible messengers. Reality, at its core, becomes a massive conversation between fields, each speaking through the language of virtual particles. What do these ghost particles do in the structure of spacetime? Some scientists say that virtual particles might add to vacuum energy, which is the energy that empty space is made of. He thought it was a mistake when he added the cosmic constant to his models. But after many years, studies of dark energy, the force speeding up the growth of the universe, made that word useful again. Also, guess what? One idea for what dark energy might be is the energy from virtual particles in the void. But there's a massive problem. When we calculate the vacuum energy from quantum field theory, the numbers are horrifyingly wrong, off by a factor of 10 to the power of 120. That's the most off-the-mark prediction in the history of physics. If we're ever going to understand dark energy, quantum foam, or the true structure of reality, this vacuum mystery has to be solved. Some people even go so far as to say that quantum changes could explain the whole nature of spacetime. It's possible for the shape of space to come from the reactions between virtual particles, not the other way around. This would happen if there are enough of them. In this light, the void is not a place where science can happen. The vacuum plays the part. It's also possible that virtual particles link to deeper theories like string theory or loop quantum gravity. In those models, space isn't continuous, it's granular or woven. Virtual particles might be symptoms of how those tiny threads are vibrating, bending, or slipping out of alignment. In that case, every ghost particle could be a ripple in a deeper, invisible ocean of geometry. Some theories even think that these changes could cause virtual black holes, which are like tiny black holes that form and disappear in unbelievably short amounts of time. If that's true, then empty space is full of tiny singularities, which are flashes of crazy gravity forces that happen in the blink of an eye. The Planck length, the smallest real thing. Get a ruler. They're called virtual particles, and even though they're not real, scale that tells you to do so. There is a limit called the Planck length, which is about 1.6 times 10 to the minus 35.5 meters. It's 10 times smaller than a proton, to give you an idea. A proton is about the size of the world that we can see. The Planck length is about the size of a tree. We're going that deep. Named after the physicist Max Planck, this is not just a number, it's a boundary, a wall, a line across which our current laws of physics fall apart. Below this scale, we can't rely on general relativity to describe space, and quantum mechanics starts breaking into static. This is where reality might stop being continuous and start being quantized. What does it mean, though, that the Planck length is the tiniest real thing? It means that space itself could be broken up into pixels. There may be basic units in space, like pixels in your phone screen that you can't see. These are pieces of volume that can't be broken down any further. That's not possible on your screen. Also, in real life, you might not be able to go half a Planck length. There isn't a smooth flow. There is only a grid that is too small for us to see. This idea comes from putting Einstein's theory of general relativity and quantum physics together. Classical physics says that you can measure places with an infinite level of accuracy. Quark physics says you can't. Heisenberg uncertainty means that you can never be sure of both a particle's place and its speed. Add gravity to the mix now. If you try to measure a particle's position with extreme precision, you need high energy to resolve those tiny scales. But put too much energy into a small space and, boom, a black hole forms. That black hole swallows the thing you were trying to measure. The result? There's a fundamental limit to how precisely you can slice space. And that limit is the Planck length. This is also the length scale at which quantum gravity, the mythical unifying theory of everything, must operate. Whether it's string theory, loop quantum gravity, or some other yet undiscovered framework, all of them aim to make sense of what happens at or below this bizarre threshold. The Planck length comes from combining three key constants of nature. Planck's constant, which controls how particles behave at the quantum level, the speed of light, which sets the rules for relativity, and the gravitational constant, which defines the strength of gravity. Together, these create a tiny unit of length that represents the smallest meaningful scale in the universe. They make a unit of length that has nothing to do with human scale numbers when you add them together. It's not about rules or light years. It has to do with the universe's own code. Planck length is built into the way things work in the real world. Some types of loop quantum gravity think that space is made up of very small loops, also called spin networks. and that the area and volume are quantized. You can't just pick any shapes or sizes. They have to fit into certain values, like Lego bricks. How small are those bricks? Structures on the Planck scale. This means that space is not a flat sheet, but a quantum web made up of separate cells. String theory, on the other hand, suggests that the fundamental strings vibrating to make particles can't be probed below the Planck length. Try to zoom in more, and the string snaps back. The physics loops around. So even if space isn't pixelated per se, our access to it is blocked below that size. Why does this matter? Because it tells us something profound. The universe has a resolution limit, a cosmic grain, a boundary of knowability. It's the end of the road for classical thinking and the launchpad for every theory that tries to explain how gravity and quantum mechanics coexist. It might also have something to do with information theory. Some experts think that you can't fit as much information into a space smaller than a Planck length without it turning into a black hole. This has to do with the Bekenstein bound, which says how much information can fit in a certain area. This limit is real at the Planck scale. Not only is it about space, but also about what we know. If reality does have a pixel size, then even the vast smoothness of the cosmos, the orbits of stars, the curvature of galaxies, might just be the low-resolution projection of something granular and primal. Imagine the universe as a video game. At a distance, it's cinematic. Up close, it's polygons and code. We might never be able to see the Planck scale for ourselves. It's not secret. It's that the energy needed to look for it would turn into a black hole and swallow the experiment up. It's the worst kind of catch-22 in nature. Zero-point energy, the universe's ground hum. Think about turning everything off, nothing to see, move, or heat up. Even if you cool a machine all the way down to minus 273.15 degrees Celsius, it is still not quiet. It's shaking. Not really, but it's clear. Zero-point energy is that last bit of buzz, that weak and unchangeable jitter in the quantum field. It could be the strangest sound in the whole world. Zero-point energy exists because of the uncertainty principle. In quantum mechanics, even when a system is in its lowest possible energy state, the so-called ground state, you can't eliminate all motion. Position and momentum can never both be precisely zero. That means every particle, every field, and every point in space still holds some residual energy, even at the coldest, calmest limit of nature. No, this is not just theoretical filler. It can be measured. In 1948, a Dutch scientist named Hendrik Casimir made a very bold prediction. If you put two metal plates that are not charged very close to each other in a vacuum, they will stick together, not because of static electricity or magnetism, but because of the quantum vacuum itself. There is a change in pressure because the energy of virtual particles in the vacuum is a little different between the plates than it is outside them. Since then, studies have shown that this force, which is now called the Casimir effect, exists. It is direct proof that zero-point energy exists. Zero-point energy might not be such a small thing after all. It could be everything. If you figure out how much zero-point energy is in just 1 cubic centimeter of space, the answer is terrifying. You can get amounts as high as 10 to 120 joules per cubic centimeter, depending on how you cut the numbers. The room inside a sugar cube holds more energy than all the stars in the sky that can be seen. Why don't we see that then? Why isn't the world just a sea of quantum fire that's on fire? That's the vacuum disaster, which is a name that scientists only half joke about. We got the wrong answer for vacuum energy from quantum field theory by the biggest amount in the history of science. There's something missing. It's either not possible to understand how zero-point energy works with gravity, or the math is wrong. Now let's talk about dark energy. Astronomers found out in 1998 that the universe is getting bigger and bigger. There is an unseen, consistent, and very strange force moving galaxies apart. The best person we can find? A steady energy that fills the place even when there is no matter there. To put it another way, zero-point energy. Is that true? If so, The quiet hum of empty space could be what's making the universe bigger. Not weight. Doesn't matter. It's just the vacuum, speaking softly and tearing the world apart. But zero-point energy might not just be in the universe, it might also be inertial. One disputed idea says that inertia, which is the resistance of things to acceleration, could be caused by the zero-point field. From this point of view, pushing something means pushing against a sea of empty energy. That pushback is what we think of as mass. This is a beautiful thought, and if it were true, it would change the basic rules of Newtonian motion. There are even speculative proposals for zero-point energy extraction, the sci-fi dream of pulling usable energy from empty space. Devices called quantum vacuum thrusters or Casimir batteries have been proposed, though no credible mechanism exists to harvest zero-point energy without violating conservation laws of thermodynamics. For now, the hum stays locked. Zero-point energy contributes to the Lamb shift, an observable change in the energy levels of hydrogen atoms caused by interactions with the vacuum field. It's not just a theory, it's a correction that matches reality down to decimal places. It also factors into spontaneous emission, where an excited atom drops energy by emitting a photon nudged by fluctuations in the zero-point field. In quantum electrodynamics, the most accurate physical theory ever devised, zero-point energy is unavoidable. It's baked into every calculation. Without it, the math collapses. Without it, atoms don't work. What if the zero-point energy is only the stillness on the top of something more fundamental? What if this jitter is just white noise coming from a speaker? Not chance, but a stronger signal we haven't figured out yet. Some people think that the energy in the vacuum might be organized, that there might be order beneath the chaos of virtual particles and quantum jitter, hymns that are hidden, frequencies in geometry. It's possible that this isn't just background noise. It could be a carrier wave sending the universe's most basic rules. That idea ties into theories like the holographic principle, or models where space and time themselves emerge from quantum information. In those pictures, zero-point energy might be the first note played by the universe, the residue of information being woven into spacetime. Some people believe that the vacuum is not really the ground state, that we live in a fake vacuum, a state that is neither stable or unstable, but sits on top of a more stable version of reality. If zero-point energy is only a brief peak, then the vacuum could decay and space would change into a more stable shape at some point, maybe tomorrow or in 1 trillion years. That would get rid of everything, right away. Not a warning, no memory at all. The Higgs field, space has mass too. How about the idea that particles don't have mass, but instead interact with it? The Higgs field is a strange idea. It's a force field that covers all of space like an unseen fog and doesn't push or pull like gravity or electromagnetic fields. It's everywhere. It never changes. The force that makes massless particles into the building blocks of everything you see, touch, or experience. Discovered theoretically in the 1960s and confirmed experimentally in 2012 with the detection of the Higgs boson at CERN's Large Hadron Collider, the Higgs field is a cornerstone of the standard model of particle physics. But we rarely talk about what it feels like, what it is, what space becomes when this field is part of its structure. Think about swimming in honey. That's what particles feel when they pass through the Higgs field. Photons and other massless particles just slide right through. Some, though, like electrons and quarks, get stuck when they interact with the Higgs field. They feel more stuck and gain more mass the stronger the contact. In other words, mass is drag. It's not an intrinsic property, it's a relationship. A particle with zero Higgs interaction moves at light speed. A particle with a strong interaction slows down and gains weight in the universe's frame of reference. You're heavy not because of your atoms, but because your atoms can't ignore the Higgs fog. We have to rethink how we think about space because this is crazy. A field is usually thought of as something that lives in space, but the Higgs field is in space. It's a pattern that covers everything. It can't be turned off. You can't get around it. The Higgs field is still there even in deep space, where there is no matter, radiation, or dust. Always on. One thing that makes it stand out is that its vacuum expectation value is not zero. In science terms, that means the Higgs field isn't zero even when it has the least amount of energy. When nothing is done to them, most fields go back to zero. Higgs doesn't do that. This breaks a basic symmetry in the rules of nature. This is called random symmetry breaking, and it's this break that makes mass possible. Now, why does this matter for how reality is put together? Since there would be no fundamental particles without the Higgs field, they would all have no mass. That means there are no stars, atoms, or science. Particles with no mass would move at the speed of light and never slow down enough to stick together. The universe would be made up of nothing but radiation, which would be structureless, dead, and cold in a different way. The Higgs field is kind of what makes things possible. A field is not enough to have matter. It must also have a field. At about 125,000 giga-electron volts, or about 1.3 times the mass of a proton, the Higgs boson, which is the quantum of the Higgs field, is extraordinarily heavy. It's also unstable, breaking down almost right away into smaller pieces. It does, however, point to the greater truth of the field that sits beneath it. A field that we can't turn off and that may have structure, change, and even texture at the quantum level. Could the Higgs field ripple or tangle beneath the surface of spacetime? Some physicists believe that just like magnetic fields form domains or patches, the Higgs field might vary slightly at ultra-small scales. That could mean tiny regions of space where the stickiness is different, altering how mass behaves, how particles clump, or even how time flows. It hasn't been proven yet, but the possibility opens the door to a new understanding of what lies beneath our reality. What if the current state of the Higgs field isn't permanent? Some calculations suggest that our universe lies in a metastable state, a false vacuum, perched precariously on a hill that could eventually collapse into a more stable configuration. If that ever happened, the Higgs field would shift. Particles would suddenly gain or lose mass. Atoms would fly apart. Physics itself would rewrite its rules in an instant, and reality as we know it would end. Does that sound impossible? Perhaps. The math behind it makes sense, though, and it connects the Higgs field to the basic structure of reality. There's more. The Higgs field might be linked to other strange forces we don't fully understand, like dark matter or inflation. Some more general ideas say that the Higgs could have siblings, extra-scalar fields that shaped the early universe, or may even still be around in higher dimensions. In this case, the Higgs could be a small part of a bigger, more complex texture of space. When you think about mass, a rock, your body, a car, don't think of weight as something that is built in. Think of it as a bargaining process, a reaction to an unseen field that moves through space and tells particles how much drag they should carry. The Higgs field does more than just make matter. It also holds us to a certain view of the world, a world where things can stick together, where the stars can burn, where living things can start, because of a fog that we will never touch but will always pass through. Space-time crystals. Are there patterns beneath the flow of time? We've all heard of regular crystals, like diamonds, quartz, and salt. These are made up of atoms that are grouped in neat repeating designs in space. What if we switched things around, though? If something could repeat in time instead of place, what would that be? This is not a figure of speech or a running clock. It is a real structure that changes, moves, or oscillates in a loop that never ends. Space-time crystals, which are also called time crystals, are a strange world. It's not science fiction. It's true science, and labs are already running with it. Nobel Prize-winning scientist Frank Wilczek came up with the idea of time crystals for the first time in 2012. In his theory, he thought about a system whose ground state or lowest energy state was not still but moving, something that never stops moving and always has a beat, even when no extra energy is being added. That is already strange. When you look at traditional physics, ground states are calm. They're the peace after all the storms. A time crystal, on the other hand, never stops. Its silence is like a dance. At first, the idea didn't seem possible. How can something be doing if it has the least amount of energy? Don't you think that would be against the law? Why thermodynamics? But in 2016, scientists proved that time crystals are possible according to the rules of quantum physics. This was especially true in systems that use cyclic energy. Because of that big step forward, the first real-time crystal was made by a Google team in 2017 using their quantum computer. They built it out of a chain of qubits, quantum bits, driven by a laser in pulses. What they saw was wild. The qubits began oscillating, not in sync with the laser but at half the driving frequency. That means the system settled into a rhythm of its own, resisting the external push, like a dancer refusing to follow the beat and instead finding her own groove. This is called discrete time translation symmetry breaking, a fancy way of saying the system breaks the normal rules of time flow. Just like spatial crystals break translational symmetry by choosing repeating positions in space, time crystals break time's uniformity by choosing repeating states in time. What if space-time itself has this kind of structure? Not just particles or fields dancing in time, but space and time themselves, pulsing in some deep rhythm, far below the surface of what we perceive. Some physicists believe time crystals could be more than a quantum oddity. They might point to a fundamental layer of reality, one that isn't smooth, continuous space-time, but rhythmic, layered, and structured at quantum scales. Imagine space-time not as a flat sheet, but as a lattice vibrating through time like a heartbeat, a cosmic metronome. It would mean a lot if that's the case. It might help explain why time moves forward only, why there is even an arrow of time. In physics, equations are often time-symmetric, which means they still make sense when you run them backwards. We age, though, in the real world. We forget what will happen. Once eggs break, they can't be fixed. Could crystals of time build a route into the structure of time itself? Space-time crystals could connect to the early universe. Some models of cosmic inflation suggest that space-time underwent phase transitions, similar to how water freezes into ice. What if that freezing left behind periodic structures not just in temperature or energy, but in the geometry of time itself? There's also speculation that time crystals could inform quantum gravity. In loop quantum gravity and related models, spacetime is built from discrete chunks or nodes. Adding time-periodic behavior to those chunks might explain how time arises from a more fundamental timeless state, maybe even unifying the concept of time with geometry, thermodynamics, and quantum information. After that, there's tech. Time crystals could change quantum computing if they are stable and don't change. A time crystal could not decoherence because it naturally changes states in a safe and reliable way. This is different from normal systems that lose coherence quickly. That means quantum memory that lasts longer, readings that are more accurate, and maybe even quantum timekeeping that is better than anything we've seen before. Of course, there's a limit to what we know. So far, time crystals have only been made in highly controlled environments, at near zero temperatures, using ultra-cold atoms or superconducting qubits. Whether they occur naturally, out there in the cosmos, is still an open question, but if space-time is layered with periodicity, we might one day see traces, repeating gravitational signals, cosmic rhythms, or even glitches in time flow that hint at a deeper clock underneath. If you woke up every day knowing that space itself is vibrating with an unseen beat right under your feet and all around your atoms, that would be amazing. Not figuratively, but really. That the world beats to a beat that is older than time, even when there is no time. Time may not just flow then. It could be a song. We might even be able to hear the chorus if we listen carefully. Are there space-time defects, kinks in the grid? Think about instantly freezing a pond. You can see tiny flaws like air bubbles, cracks, and places where the crystal didn't form quite right if you look very closely. Use that thought in every part of the world. Space-time might have flaws too if it's like fabric. Some people have real scars on their bodies that were formed during the Big Bang. These are called space-time flaws, and they could be deep in the cosmic grid that we think is smooth. Let's go back to the beginning to get this idea. In the first few seconds after the Big Bang, the universe wasn't just getting bigger, it was also getting cooler and going through phase changes. In the same way that temperature and pressure change water into ice or steam, the basic forces of nature may have separated out from a single force during this cooling. Gravity had a split. Then there was the strong nuclear force. After some time, the electroweak force split into the weak nuclear force and the electromagnetic force. Each of those symmetry breakings may have left behind imperfections, like cracks in a cooling material. These imperfections could be topological defects in the fabric of spacetime itself, and we have names for them: domain walls, cosmic strings, monopoles, and textures. Domain walls are two-dimensional defects that form when different regions of space fall into different vacuum states. Think of it like bubbles in boiling water. Each bubble forms independently, and when they collide, a wall forms between them. In spacetime, these domain walls would represent boundaries between regions where the laws of physics might slightly differ. Cosmic strings are one-dimensional defects, infinitesimally thin, but incredibly dense and long. These are not literal strings like in string theory, but rather lines where spacetime is twisted or compressed. If they exist, they might span light years in length but be thinner than an atomic nucleus. And they'd carry immense energy. A single cosmic string could bend light like a lens, cause ripples in spacetime, and even affect galaxy formation in the early universe. Monopoles are point-like defects, single locations where a magnetic field behaves in a way it usually doesn't. In standard physics, magnetic poles always come in pairs, north and south. But some early universe theories predicted magnetic monopoles, lone north or south poles formed during symmetry breaking. We haven't found any yet, but if one were discovered, it would shake physics to its core. Then there are textures, not the surfaces you can feel, but large-scale, field-based fluctuations that could subtly warp spacetime across vast regions. These wouldn't be dense like strings or walls, but more like patches of twisted field energy, rippling out slowly across the cosmos. If these flaws are out there, then why haven't we seen them? In that case, there is a mystery. Some models say that there were a lot of them in the early universe, but that they either broke down quickly or were spread out by cosmic inflation, the very fast expansion that made the universe flat in a matter of seconds. Some people think we may have seen signs, like cold spots in the cosmic microwave background that we can't explain, or strange gravity lensing patterns that could point to a secret string. Some physicists speculate that black holes or wormholes might be related to spacetime defects. What if some extreme objects aren't just collapsed stars, but defects in the grid? Regions where geometry itself broke down or folded in on itself. We have to think about what empty space really means when we think about spacetime flaws. If the vacuum isn't really smooth, if it has old scars or leftover textures, then the universe as a whole might be shaped by things that happened a very long time ago. These flaws wouldn't just be old memories either. They could change basic factors, change the way particles behave, or cause strange things to happen like vacuum decay. To put it another way, they're not just fossils, they're active parts of the universe's ongoing development. This potential is important on all levels, even the tiny ones. There may be small bends in what we call straight lines in spacetime if it has wrinkles. Earth's gravity warping is taken into account by GPS satellites. But what if there are other, secret warps from long-dead defects that gently push photons and particles as they fly? At the very edge of theoretical physics, these flaws could be the places where different worlds meet, the holes in our space-time bubble, or doors to other dimensions and branes. Tachyon fields, ghost layers of faster-than-light physics. View yourself on a boat, sailing on a calm sea. A stream is moving faster than the boat and creating the waves above you that you can't see. That's how tachyon fields make us feel. Tachyons are made-up particles that move faster than light in theoretical physics. Based on Einstein's theory of relativity, this shouldn't be possible. But some formulae show that these things might not only exist, but also be a part of how space-time is structured. The word tachyon comes from the Greek tachys, meaning swift. These aren't just fast particles, they're always faster than light. They don't accelerate to light speed, they start beyond it. That alone turns everything upside down. Light speed is supposed to be the universal limit, the cosmic speed cap. Tachyons would blow right past that. We've never seen one. No detector has picked up a tachyon. That's because if they exist, they might be fundamentally undetectable in the traditional sense. Like shadows under the floorboards of physics, they could influence reality without ever showing their face. Why do we care about them anyway? Since they come up in math. When trying to explain systems that aren't stable in some quantum field theories, like early forms of string theory, tachyonic fields easily show up. Picture a ball on top of a hill. It is not stable. It is about to roll over. A tachyonic field can be used to describe that chance, that moment. It's not because the ball is moving quickly, but because the equations that describe its instability are similar to those that describe tachyons. In other words, tachyons might not be real things zipping around. They could be signals, mathematical indicators that the current state of a system is unstable. That's why they appear in theories about false vacuum decay, early universe inflation, and brane collisions in higher dimensional space. They represent moments when spacetime itself is on the edge of a transformation. If tachyon fields exist below or inside spacetime, they might be a part of a system we don't fully understand yet. Think of the world we know as a sheet. Under that sheet is a layer that moves faster than light. This layer is like a superfluid base that carries information at speeds that our particles can't reach. Tachyons wouldn't live in space-time. They'd live below it and shape its development without being seen. Scenes from brane worlds in string theory use this idea. What if our world is a three-dimensional brane floating in a higher dimensional bulk? Tachyon fields might show the tension between branes or how unstable their places are. Tachyons show up in the equations like cracks in the system when branes bump into each other or move apart. These cracks could change the shape of whole worlds or even cause them to crash. Some researchers believe tachyon fields could relate to dark energy, the mysterious force causing the universe to accelerate in its expansion. If the vacuum of space contains a tachyon-like instability that could explain why it keeps stretching. Others suggest that tachyons might be responsible for quantum entanglement, transmitting correlations between particles through a hidden, faster-than-light channel outside ordinary space-time. On the very edge of science, some people think that tachyons might let information slip between timescales, or be the way that effects happen before their causes. There is one thing that all of these ideas have in common. The universe may be built on top of a layer of rules that don't follow the same light speed limits that we see. Still, most scientists are still not sure about tachyons because they don't follow the rules of causality as we know them. If you include them in your theory, you might end up with paradoxes. For example, if you send a signal back in time, you could end up with the grandfather paradox, time loops, or even worse. But the fact that these things keep showing up in real numbers says that they might not be fiction after all. Could we ever detect them? Maybe not directly, but some theorists propose that tachyon condensation, a process where a tachyon field settles into a new, stable vacuum, might leave signatures like gravitational wave echoes or cosmic string remnants. Others look for patterns in high-energy particle collisions, anomalies in cosmic background radiation, or unexplained quantum behaviors. Extra dimensions curled up beneath us. From top to bottom, left to right, and forward to back, that's how space works for you. It's 4 when you add the time. What if this is only a small part of the whole picture? A lot of the most interesting ideas in modern physics, especially string theory, say that our world may have more dimensions than we can see. They're not in space either. They're right here, tucked under every rock you've ever stepped on. This idea stems from attempts to unify gravity with the other fundamental forces of nature. Gravity has always been the odd one out. It's incredibly weak compared to electromagnetism or the nuclear forces. Why? One possible answer: it's being diluted across extra dimensions we don't experience directly. In string theory, particles aren't points. They're tiny vibrating loops, and the way they vibrate determines their properties: mass, charge, spin. But those vibrations only make sense in a space with more than 3 dimensions. The most common version of string theory requires 10 dimensions, 9 of space and 1 of time. Another version, M theory, calls for 11. Where are they then? They could be squished together or curled up very tightly at sizes that are too small for our present tools to see. Think of a yard hose. From far away, it looks like a straight line. When you get close, though, you can see the circle-shaped dimension around it. In the same way, every point in our known 3D space could be the center of several hidden dimensions that are looped and twisted into forms called Calabi-Yau manifolds. These shapes aren't just abstract math. They determine the possible types of particles and forces in our universe. Change the shape, and you change the physics. That's how extra dimensions help explain why the universe has exactly the laws it does. If these dimensions are real, they could influence gravity, and maybe even hide new particles. Some theories predict the existence of Kaluza-Klein modes, echoes of known particles, but with higher masses, caused by movement through the extra dimensions. We might detect them in high-energy experiments like those at the Large Hadron Collider. Some people think that dark matter might just be normal matter stuck in another world, or that, unlike light, gravity spreads into the extra dimensions, which would explain why it is so weak in our world. There are different kinds of things, even black holes. Their forms and actions change a lot when they move to higher dimensions. You might find strange gravity monsters like black strings, black brains, or more. If the math works, some might disappear faster, fall apart in different ways, or even create paths to other layers of space. Now take this a step further. What if you are a 3D being stuck to a 3-brane, a surface within a higher dimensional space? Everything you know, all the particles and forces you experience, are confined to this brane. But gravity might leak off it, and energy could tunnel between branes. Some cosmologists even propose that the Big Bang was a collision between 2 such branes, creating our universe in the aftermath. It's like living on a soap film, floating in a larger invisible bathroom. Could we get to these scales at some point? Not quickly, but some scientists have suggested tests that would use mini black holes, graviton detection, or very accurate measures of Newton's law at very small sizes. If gravity changes over short lengths, it could mean that dimensions are curled up. Some people also think that string resonances, movements in other dimensions, and even hyperspace flight are possible. But these ideas are still very far from what we can test right now. Still, it's fun to think about them. The measures won't go away, either if they're there. They're built into every spot in space, every string sound, and every step you've ever taken. Causal sets. Is spacetime actually discrete? We picture space and time as smooth, like a river that flows smoothly, or an endless plane that goes in every direction. But what if that ease is just a trick? But what if, deep down, space and time are made up of tiny, separate pieces called atoms of spacetime? That's the big idea behind causal set theory, a scheme so different from what we think we know about how the world works that it could change everything we think we know. A simple but important question lies at the heart of this theory. Is the world continuous or discrete? In math, a line that doesn't break can be split up forever. There are an endless number of points between any two. We've learned that energy, matter, and even knowledge often come in separate pieces in the real world. Bits, photons, and atoms. So why not add time and space? Causal set theory proposes that spacetime is not a smooth manifold, but a collection of discrete elements, connected by a fundamental rule, causality. That means each element is linked to others by the possibility of cause and effect relationships. These links form a partial order, a structure that tells you which events could have influenced which others without requiring coordinates or smooth curves. Picture it like this. Instead of a canvas, the universe is more like a pointillist painting, millions of tiny dots forming a larger picture. But unlike paint, these dots represent individual space-time moments, ordered by which ones could affect the others. It's like building space-time out of dominoes, not laid in lines, but layered in webs of influence. This means a lot of things. First, it would mean that space and time don't always flow together or split up. A Planck scale grain is the tiniest space between things that where and when no longer mean anything. There would be no area to start from, so motion, fields, and even shape would come from the connections between these grains. Second, it gives us a new way to think about quantum gravity. Putting together general relativity and quantum mechanics is one of the hardest things in physics. General relativity says that gravity is the curvature of space-time, and quantum mechanics is all about doubt and chance. When people try to combine these models in the usual way, they often end up with infinities or failures. But causal set theory gets around the whole issue by not considering space-time to be smooth at all. Instead of trying to quantize a continuous geometry, it builds space-time from scratch, starting with discrete elements and causal links. Gravity, in this view, isn't a force or a field. It's the statistical behavior of a vast network of causal points. There's more to this than just vague theory. There are real equations and forecasts in the theory. One big idea is that the cosmological constant, the mysterious force that makes the universe expand faster, might come about naturally when causal sets are not ordered. The changes that happen when you add points at random to a building causal structure could make an energy density that looks like dark energy. Causal set theory is inherently Lorentz invariant, meaning it respects the rules of special relativity. Even though the structure is made of discrete parts, it doesn't single out a preferred direction or frame. That's a big deal. Most discrete theories break that symmetry. How do we test it, though? That's the tough part. They might not be able to tell the difference between a continuous and a discrete spacetime at very high energies or very short distances, which is way beyond what we can test right now. Some people think that signs might show up in the noise from gravitational waves, the coming of cosmic rays, or small problems in particle physics. Others are looking into how causal set theory might leave marks in the cosmic microwave background, which is the light from the very beginning of the world. There's also a philosophical dimension. If space-time is made of discrete elements, then there's a limit to resolution. Just like pixels on a screen, there's no smaller detail beyond the minimum. That could mean the universe is fundamentally digital, not like a computer simulation, but governed by finite, countable rules rather than infinite smoothness. Some people say that causal set theory doesn't have any direct evidence to back it up and has trouble reproducing all the details of general relativity in complicated situations. However, people who support it say that it is one of the few real models of quantum gravity that starts with causal structure, which is a key part of relativity, and builds from there. Everything we know, the stars, the fields, and even the idea of space itself, might have come from a complicated web of cause and effect links, a picture of space, a web for everyone. That's not just beautiful writing, it could be the most accurate picture of life. Spin networks, twisted threads holding reality together. Think about being able to zoom in so much that space-time starts to break apart. Not into bits or fields, but into knots, into tiny points and connections that make up a quantum spiderweb below the smooth world we see. That's the world of spin networks, which is the main idea behind loop quantum gravity, a top theory that tries to answer the question, what is space made of, that Einstein couldn't. Geometry needs to be rethought in order to understand spin networks. Classical physics sees space as a stage that is continuous, passive, and can be split up indefinitely in many ways. Due to general relativity, that stage was bent. It was shaken by quantum physics. Loop quantum gravity, on the other hand, says that the stage is made up of quantum states. These states aren't strings or points. They are loops, which are closed lines that store shape information. When you join these loops, you get a spin network, which is a graph of nodes, points, and lines, connections, each marked with a quantum number that shows the angle, area, or volume of the point. It's kind of like a space Lego set. Each point in space is a node. Each edge tells you how those points connect to each other. They make up a framework of mathematics when put together. This shape isn't smooth though, it's quantized. Space doesn't stretch out forever. It's made up of separate pieces. A measure of space, a measure of space. There is no middle ground. Spin networks were first introduced by physicist Roger Penrose in the 1970s and later expanded into a full theory by researchers like Carlo Rovelli and Lee Smolin. They realized that these networks could evolve over time, becoming what's called a spin foam. It's not just space that's made of loops. Spacetime is a foaming sea of ever-changing networks. We might come to crazy conclusions from this. For starters, it seems to show that the Big Bang wasn't a singularity. It's possible that the universe began with a spin network with very little volume instead of a point with infinite density. A very small piece of space that is not zero but has a limit. There is no need for singularities, no very high populations. Second, it means that time might not be fundamental. Spin networks don't evolve in time the way we expect. Instead, time emerges from their changes, from differences between one configuration and the next. In this view, time is not a river, it's the rhythm of network transitions. These transitions don't need space-time to happen. The network itself is the space, and its changes are the passage of time. It's like saying the music is just the changes in notes. You don't need a separate stage for it to play on. What can we learn about gravity from spin networks? Plenty. Gravity isn't a force or a field in loop quantum gravity. It has to do with the shape of the spin network. Einstein talked about curvature, which is just the way these loops and nodes are set up. Mass and energy don't bend space. They change the way the network is set up. It's like pulling on a net. The shape changes, and things move in it in new ways. Q-bounce is one of the most interesting ideas. Black holes might not collapse into singularities. Instead, they might reach their smallest size and bounce off of other things, turning into white holes or starting new worlds. In the same way, the early universe might have shrunk before expanding again. This is an option to the usual Big Bang theory. Another prediction: discrete spectra for areas and volumes. If spin networks are real, then the area of any surface, say a black hole's event horizon, should come in quantized chunks. That leads to a beautiful connection with black hole entropy, helping explain why black holes contain the information they do. How do we test this though? That's tough. On the Planck scale, which is between 10 and minus 35 meters, these patterns can be seen. Scientists are looking into possible observational hints, such as small changes in gravitational wave signals, possible marks in the cosmic microwave background radiation, or even changes in how black holes behave. Some loop quantum gravity models also say that Lorentz invariance will be broken at very high energies. Particle accelerators of the present and future might be able to find these violations. Critics argue that loop quantum gravity doesn't yet explain matter very well. It's a geometry-first theory, but newer models are working to incorporate particles and forces as additional excitations on top of the spin network, like patterns riding on a vibrating drumhead. Gravitons, the hypothetical carriers of space-time ripples. They were heard. Black holes merging in the deep dark, causing waves through the fabric of space-time, can be heard as faint echoes, waves of gravity. When they were found for the first time in 2015, they proved Einstein's prediction from 100 years earlier and gave us a whole new way to look at the world. On the other hand, and this is strange, we have measured those waves but still haven't found their basic particle, the graviton. What does a graviton really mean? Why does it matter? We know that every force has a carrier in quantum field theory. Photons are what make light possible. What is the strong nuclear force? Gluon. The weak force? There are W and Z bosons. One can be found in the Higgs field too. Quantum messages are these carriers. They are energy packets that send forces through space. If gravity is a force, it should have a way to talk to us. That's the pull of gravity. Gravitons are theoretical quantum particles that would carry the force of gravity. They're proposed to be massless, just like photons, and to have a spin of 2, a characteristic that would match the observed behavior of gravitational waves. But unlike photons, gravitons are tied to the shape of spacetime itself. They don't ride in the background. They are a disturbance. That is what makes them strange. In the event that gravitons exist, they would be geometric waves or movements of the stage, not people acting on it. We've never seen one, not right away, not even close. Why? Because compared to other forces, gravity is very weak. It is possible to lift a paperclip above Earth's gravity with just a small magnet. So, a single graviton would be so weak that it's almost impossible to find with the technology we have now. It would take a lot of energy to separate or deal with one, probably more than any experiment could handle. Gravity becomes significant only at cosmic scales, while quantum effects dominate the microscopic. Gravitons live in that no man's land in between, the realm of quantum gravity. And that's a realm we haven't fully entered yet. They still haven't given up, though. In a lot of ideas about quantum gravity, gravitons are present. In string theory, for example, gravitons are thought to come from the movements of closed strings. In this model, different particles are linked to different string movements. What is graviton? It's a certain kind of energy that has no mass and spin too. This is important because it brings together gravity and quantum physics. If string theory is true, gravitons are necessary for everything to work. The math already takes them into account. Even if gravitons exist mathematically, they still need experimental validation. And so far, there's no definitive way to detect them. Some physicists propose that gravitational wave observatories like LIGO and Virgo might one day spot quantum noise, tiny deviations in the wave signals that hint at an underlying quantum particle. Others look to the cosmic microwave background, hoping that ancient gravitational interactions left behind a quantum fingerprint from the early universe. Another approach is to hunt for graviton emission in particle collisions. If two high-energy particles interact and a graviton is emitted, some energy would mysteriously vanish, carried away by this undetectable quantum. But again, the energy scales needed to even maybe do this are far beyond what the Large Hadron Collider can achieve. Even so, the idea of the graviton is still very important. Why? Because we wouldn't have a full picture of life without it. There are two very important theories: general relativity, which explains how the world works on a big scale, and quantum mechanics, which describes how very small things work. They look great by themselves, but when put together, they don't go well. There must be a graviton or something like it in a quantum theory of gravity. Gravitons could explain how black holes evaporate via Hawking radiation. They might show how information escapes extreme gravitational zones. They could even be the key to reconciling time's arrow with quantum reversibility. They are the missing piece that could connect geometry and quantum logic. What if we never find them? Also, that tells us something. In a theoretical sense, it could mean that gravity isn't even a force. It could be emergent, like weather, which means that it comes from more basic mathematical rules. If not, you won't be able to find my graviton. The false vacuum hypothesis. A hidden layer ready to collapse. There is something in space called vacuum that holds everything you see, touch, and breathe. Not nothing, but the state of quantum forces with the least amount of energy. The state of matter at rest. The beginning of the world. Or is it? According to the false vacuum hypothesis, our universe might be living a lie. What we think of as the lowest energy state, the vacuum of space-time, might not be the true vacuum. It might be a false minimum, a stable-looking but ultimately temporary state. And if that's true, then somewhere, sometime, a catastrophic chain reaction could rewrite reality itself. In quantum field theory, a vacuum isn't nothing. It's the field at its lowest energy configuration. But sometimes, fields can get stuck in local minima, stable valleys in their energy landscape. Imagine rolling a ball into a valley. It settles and sits still. But unknown to you, there's a deeper valley nearby, a true minimum. Your ball is stable, but only until something kicks it hard enough. Yes, that is a fake vacuum. Now use this thought to think about the Higgs field, which is the unseen field that gives particles their mass. When scientists found the Higgs boson in 2012, they learned that its mass, about 125 giga-electron volts, makes it possible that we are in a false vacuum. The Higgs field and the top quark have been used in calculations that show that the energy level we are in is metastable. It's fine for now, but not for good. At a lower energy level, there might be a real vacuum. And what if we ever get to that state? The results would be terrible. The moment a true vacuum bubble forms, it would expand at the speed of light, obliterating everything in its path. Physics itself would change. The laws of nature, forces, particles, even the dimensions of space could be completely rewritten. No warning, no escape. Does that sound scary? Yes, it is. But it's also strangely interesting. It's not just science fiction that this possible situation could happen. It comes up easily in normal physics. Quantum tunneling could cause the shift if the void is not real. It might only take a chance change, a high-energy cosmic ray, or a very rare quantum event. Some theories think this may have already happened, and that a vacuum bubble may be growing right now somewhere in the universe. We would never see it coming, though, because it moves at the speed of light. For a moment, you are here. One moment, you're in a world with very different rules. Cosmic inflation, the rapid expansion that occurred after the Big Bang, might have left imprints in our current vacuum structure. Some suggest that inflation locked us into this metastable state. Others think the true vacuum might be so deep, the transition probability is vanishingly small, making our current vacuum effectively stable for trillions of years. There's also the anthropic argument, the idea that if vacuum decay were common, we wouldn't be here to wonder about it. So maybe we live in one of the few universes where it hasn't happened yet. Still, researchers keep searching for signs. Precise measurements of the Higgs boson, the top quark, and the cosmic microwave background could offer clues. If we can pin down their properties, we might better map the energy landscape of the vacuum. Meanwhile, speculative extensions of the standard model, like supersymmetry, could alter the vacuum structure entirely, potentially restoring full stability. What if not? Then everything you know, every molecule, star, and law might one day be replaced by a kind of science we can't even begin to understand. There are no more atoms, not any more light, no matter what strange truth lies below. Entanglement, threads that stitch space together. It was what Einstein called spooky action at a distance. Two particles that are light years apart are connected instantly in some way. If you change one, the other will react, not a signal. Don't wait, just stay connected. Quantum entanglement is a strange effect that has confused scientists for a long time. What if, though, entanglement isn't just a strange quirk of quantum mechanics? What if it's the base of space itself? In classical physics, space is the backdrop, a giant stage on which matter and energy do their thing. But quantum theory hints that space may not be fundamental at all. Instead, it might emerge from something deeper, something relational, something like entanglement. Entanglement means that the state of one particle is tied to another. Not just similar, linked. Their properties are interdependent, even if they're separated by entire galaxies. This doesn't mean information travels faster than light. Rather, the two particles share a single quantum state. In the past few years, scientists have been looking into an amazing idea. Space itself, the distances, the geometry, the very structure of reality, might be made out of these complex connections. This is how you can think about it. Particles that are entangled know something about each other. They talk about things. And when a lot of particles get jumbled up, they make a network of connections. That network might be space itself, not just somewhere in space. This is the heart of what's sometimes called the ER=EPR conjecture. Coined by Leonard Susskind and Juan Maldacena, it suggests that Einstein-Rosen bridges, aka wormholes, and Einstein-Podolsky-Rosen pairs, aka entangled particles, might be two sides of the same coin. In this framework, a wormhole, traditionally thought of as a tunnel through spacetime, is equivalent to a pair of entangled particles. If that's true, then every bit of space might be stitched together by hidden threads of entanglement. Even more radical? Some theories suggest that the entanglement entropy, a measure of how entangled different regions of space are, actually determines the curvature of spacetime. That is, the strength and pattern of entanglement gives rise to geometry itself. This changes the story. Space is not what holds entanglement. Entanglement is what makes space. It gets worse after that. Addis-CFT correspondence is a strong idea from string theory that says a universe with gravity in anti-de Sitter space is the same as a universe without gravity on its edges. When there are two of these, the form of the mass spacetime comes from patterns of entanglement in the border theory. This leads to tensor networks, which are mathematical tools that show how coupling makes dimension. Think of a web of quantum systems that are all connected to each other, like a grid made of pure relationships. There is more room as you move across the network, as there is more coupling. Shorter lengths mean less complications. No tangled up, there is no link at all. It's not just theoretical. In simulations using quantum systems and condensed matter, researchers have built models where space-like structures emerge entirely from entangled data. There are even black holes playing. The famous black hole information conundrum, which asks how information can get out of black holes, might be explained by realizing that Hawking radiation is connected to the inside of black holes. The entanglement network changes as evaporation goes on, keeping information safe in a secret, spread-out way. This view of space as emerging changes what reality means. It means you're not in space. You are a part of a quantum network where people share data. Your place isn't set in stone. It depends on how you connect to everything else. When it comes to space, the closer you are to something, the closer you are to it. The world turns into a huge web, and mathematics helps us tell stories about the links. And maybe, just maybe, time itself emerges from how entanglement changes. There's still so much we don't know, but if space comes from entanglement, then maybe the true fabric of reality isn't matter or energy, but relationship. Non-commutative geometry, a blurry picture of spacetime. If you look deep enough into spacetime, it should look smooth, like a calm sheet stretched across the universe. That's what Einstein thought it would look like, a gentle curve made by mass and energy. But things aren't smooth in the quantum world. Things become less clear. Coordinates might not even work the way you think they do at the tiniest sizes you can think of. Welcome to non-commutative geometry, a field of physics and math that tries to explain why space and time might not work at the Planck scale. Going 1 unit in x and then 1 in y will get you to the same place as going 1 unit in y first and then x. This is called classical geometry. The activities move around. They don't depend on the order. In quantum physics, though, this isn't always true. Position and speed are two examples of pairs of numbers that don't change. One is affected by measuring the other. It's written in the famous uncertainty principle by Heisenberg. Non-commutative geometry applies this concept to space itself. What if the coordinates of space, x, y, z, don't commute at ultra-small scales? What if measuring x and then y gives you a different result than measuring y and then x? In such a framework, position becomes inherently fuzzy. There is no exact point, only probability clouds of where things might be. This idea gained traction from Alain Connes, a mathematician who developed a formal system for non-commutative spaces. His work has been used to reframe the standard model of particle physics, potentially merging it with general relativity in a novel way. If spacetime is non-commutative, then the very structure of reality is quantized. Not just in the sense of discrete values, but in the logic of how space behaves. Geometry itself becomes an algebra of operators. Instead of points, you get spectra. Instead of distances, you get expectation values. It's like the universe is playing jazz instead of classical. Physicists exploring quantum gravity and string theory often encounter non-commutative spaces. In certain versions of string theory, the endpoints of strings are constrained to branes, and those branes naturally follow non-commutative rules. That is, the space on the brane doesn't behave normally. It's blurred, uncertain, rule-breaking at the quantum level. This could explain why we haven't been able to unify gravity with quantum mechanics. Maybe we've been trying to do smooth math on a universe that isn't smooth. Maybe gravity's failure to quantize comes from assuming commutative rules where none exist. There's also a useful point of view. The infinites that bother quantum field theory might be tamed by models that don't work with commutative ones. Small interactions can lead to mathematical blow-ups, which are results that are too good to be true. As long as space is fuzzy, though, those connections get lost and the math might work. In a world that doesn't work like a switch, even black holes might be different. Some experts think that singularities, which are the cores that are infinitely dense, might not exist at all. Because space isn't perfectly smooth, it wouldn't fall into a true point. Instead, it would turn into a dense but limited area. It also impacts cosmology. The early universe, before inflation smoothed things out, might have been ruled by non-commutative effects. Tiny fluctuations magnified into galaxies could carry signatures of this early quantum weirdness in the cosmic microwave background. How would we test it then? That's the tough part. When you get close to the Planck length, which is about 1.6 times 10 to the minus 35.5 meters, non-commutative events start to happen. That is ridiculously small. It is too far away for any collider or monitor to reach. But secondary effects, such as changes in gamma-ray bursts or strange things that happen when gravitational waves travel, might point to this secret structure. Branes, multidimensional surfaces beneath our own. Consider our universe as a thin slice, like a soap film floating in a huge unseen ocean. That's what brane theory is all about. It's based on the complex math of string theory. It means that all the matter and energy we can see is contained within a membrane, also called a brane. Other dimensions, forces, or even whole worlds are said to be moving around or next to us. In string theory, particles are not point-like, they're tiny vibrating strings. And these strings aren't limited to our familiar 3 dimensions of space and 1 of time. They can extend into 10 or even 11 dimensions. But then arises the obvious question: if there are so many dimensions, why don't we see them? One answer is the brane theory. Our universe could be a 3-brane, which is a 3-dimensional surface. Electrons, quarks, and all the other particles in the standard model could be thought of as open-ended strings with ends connected to this brane. In other words, they can only move along the brane. We can only feel space and time inside our membrane. It's like how bugs moving on paper don't know there's a 3rd dimension above or below them. Gravity, however, might be different. Gravitons, the hypothetical quantum particles of gravity, are closed-loop strings. Unlike open strings, they aren't confined to the brane. They can drift off into the bulk, the higher dimensional space beyond our universe. This might explain why gravity is so much weaker than other forces. Most of its influence leaks into the bulk, leaving behind only a faint whisper of its true strength. This has very important effects. There may be other branes floating in the mass that are parallel to ours. For each one, there could be a separate world with its own particles and physical rules. We could be a slice of a multiverse that goes on and on. The spaces between branes could be millimeters wide or as short as the Planck length. For example, The Randall-Sundrum scenarios use twisted geometry to show how extra dimensions stay hidden while still having an effect on the world we can see. In these arrangements, brains are put inside a 5-dimensional space that curves in a strange way. When the brain warps, gravity is concentrated near it, making it look weaker as you move away. In other words, the geometry of the universe isn't flat like a pancake. It's curved and rippled like a folded blanket, with brains layered in ways we can barely imagine. There's even speculation that the Big Bang itself was caused by 2 brains colliding. In such a brain cosmology, the violent impact would release energy, ignite expansion, and create the conditions for stars, galaxies, and life. This idea gives the Big Bang a cause, something it notoriously lacks in classical cosmology. If brains are real, could we ever detect them? Maybe. If gravity spreads into the bulk, then extremely precise measurements, like those from LIGO or gravitational lensing surveys, might reveal small discrepancies that hint at hidden dimensions. Particle accelerators like the Large Hadron Collider have also looked for missing energy that could indicate particles slipping into extra-dimensional space. What if 2 brains got close enough to affect each other? Could we detect gravitational ripples from an unseen neighboring universe? Could particles briefly jump from one brain to another? Could consciousness, or something like it, somehow resonate across layers of the bulk? Even though it all sounds like a guess, brain theory gives a beautiful reason for why the world looks the way it does, and why we might not be able to see a deeper structure below it. It's possible that we're not at the center of everything. It's possible that we're just riding a wave, a world that floats in a huge folded universe. And just maybe, beneath us is a whole different kind of place, one where time moves in a different way. Preons are quarks made of even smaller stuff. We're told that quarks are very important. They are the building blocks of all matter, along with leptons like electrons. But history says something else. As soon as experts thought they had found the tiniest thing, something even smaller would appear out of nowhere. Atoms. Next came neutrons and protons, then quarks. So why stop now? Preons are hypothetical particles, proposed components of quarks and leptons. The idea is that what we call elementary particles might actually be composites of even tinier ingredients. If true, it would mean that our current standard model is just another layer in a deeper onion. Why even say there are preons? Redundancy is a big reason for this. The standard model has a lot of particles and factors whose masses, charges, and mixing angles don't make sense. How come there are 3 types of quarks and leptons? What makes their mass ratios unique? Why are the weak force connections set to these values? Models of prey try to clean up the mess. Different ideas try to explain the wide range of quarks and leptons by saying that they are all just different mixtures of preons. Think of it like how protons and neutrons are made of up and down quarks. What if up and down quarks themselves were made from 2 or 3 types of preons in different configurations? In this view, a top quark, the heaviest of the bunch, might be like a dense cluster of preons, while an electron might be a looser, simpler arrangement. The variety of particles would stem from preon binding energies, internal spin structures or interaction patterns. High-energy experiments, like those at the LHC, haven't shown any internal structure to quarks or leptons. They appear point-like, even at scales smaller than 10 to the minus 19 meters. No scattering anomalies, no internal jitter, just clean, smooth particles. They still haven't given up, though. Some preon models say that the internal structure only shows up at very high energies, which are much higher than what modern colliders can do. Some people say that preons aren't limited by normal forces, but by new reactions that only happen at very short distances. Some models propose preon strands or strings. Rather than point particles, preons might be tiny loops or filaments. Their geometry could determine particle properties like mass and charge, much like how string theory uses vibration modes. Some preon models even say that there will be new particles, or hybrid states that haven't been seen yet. It would be proof of preonic structure if one of these showed up in a collider. There's also an interesting philosophical idea in this. We can't depend on the standard model if preons are real. It's coming up. It's possible that the whole field of particle physics comes from a lower level than we can see right now. Just like science comes from atoms, and atoms come from nuclei and electrons. What's under preons if there's something under quarks? Are we looking for a system that goes back in time forever? Is there something smaller all the time? At what point does it stop? Maybe at the Planck scale, where particles turn into pure geometry, space-time knots, or quantum information patterns. We're not sure. The search goes on though. Lattice space-time, a universe built like Minecraft. If you zoom in enough, the smooth area might not be smooth at all. What if space-time isn't a single field but is made up of tiny, separate pieces like pixels in a picture or bricks in a wall? This is the idea behind lattice space-time, a theory that says the universe is mainly digital and is made up of a four-dimensional grid where space and time are split into units that can't be split up. In this model, particles don't move smoothly. They jump from one node to the next. Just like a character hopping through Minecraft blocks or a light beam tracing through a pixelated screen, every movement is a series of discrete transitions. You can't go between points because there's no such thing. This concept isn't just sci-fi speculation, it's a useful framework in modern physics. Lattice quantum field theory is already used in particle physics to simulate interactions in a discretized spacetime. It's how we model complex processes like quark confinement and nuclear binding. But these are computational tools. What if the lattice isn't just a shortcut for math, but a reflection of physical reality? If spacetime has a minimum resolution, like the Planck length around 1.6 times 10 to the minus 35 meters, then treating it as a grid makes sense. You wouldn't expect water to behave continuously if you zoomed in to see molecules. Maybe the universe works the same way. A lattice structure could also naturally explain why particles exist as quantized units. In a digital universe, certain wave functions only fit on the grid, much like certain standing waves fit inside a stringed instrument. That would explain why particles have specific, discrete masses or charges. They're the allowed patterns that can exist on the universal lattice. Then there's the matter of balance. Keeping Lorentz invariance, which means that the rules of physics look the same to all viewers, no matter how fast they are moving, is one of the hardest things about lattice models. Grids naturally point in certain ways. Forks are with them. However, spacetime does not. At the very least, it shouldn't. To get around this problem, some thinkers suggest random or fuzzy lattices, also known as causal sets. In these, the grid doesn't have tight rows and columns, but there are still clear steps. Some people say that Lorentz invariance is emergent, which means it's not a basic feature but something that happens statistically at big scales, like how a crowd looks fluid even though each person is separate. There are even hypotheses where particles are topological defects in the grid. Think of a kink in a rope or a whirlpool in a fluid. The particle isn't a thing, it's a pattern in the lattice. In this view, mass, spin and charge arise from how the defect twists or loops through the nodes of spacetime. If the universe is a lattice, then it's countable. There are only so many positions a particle can occupy, only so many energy levels it can jump between. It brings physics closer to computation, where everything is finite, rule-based, and in theory, programmable. This brings up an interesting question. If the world is digital, does that mean it's a simulation? Some scientists, like Stephen Wolfram, have looked into the idea that reality is a cellular automaton, which is a very large computer system with rules that changes over time. Here, the grid is like the computer's wiring, and the universe is what it makes. Do we feel like characters in a cosmic drawing engine? We're not sure. However, tests are being thought of to see if this is true. Some people look for anisotropies or changes in direction in very high-energy cosmic rays that could reveal a grid below. Some people look for noise patterns in data about gravity waves that might show digital jitter at the Planck scale. Gravitational vacuum condensate, a superfluid view of spacetime. Could it be that gravity isn't really a force, but just the result of a stream we're all moving through? It may sound strange, but in some models of theoretical physics, spacetime acts like a superfluid, which is a strange, frictionless material that has quantum qualities. We're not just using metaphors here. The gravitational vacuum condensate theory is a real structure that can be tested. In quantum field theory, a vacuum condensate is a ground state of a field where something, energy, particles, or even fields themselves, takes on a collective, organized form. It's not empty, it's not quiet, it's structured. And in this case, the idea is that the vacuum of spacetime itself is such a condensate, possibly of gravitational degrees of freedom. In condensed matter physics, superfluids like helium-4 can flow without viscosity. They can climb walls, swirl in quantized vortices, and defy classical behavior. Now apply that same weirdness to the fabric of space. What if, at extremely small scales, the vacuum is a gravitational superfluid, constantly in motion, but appearing smooth to our limited instruments? This opens up new interpretations for phenomena we already observe. Gravitational waves could be ripples in this superfluid medium. Black holes might be phase transitions, regions where the fluid reaches a critical density. And the curvature of spacetime we associate with gravity could be emergent behavior, like surface tension on a fluid surface. The core idea is that Einstein's general relativity is an effective theory, a macroscopic approximation of deeper, microscopic dynamics in the condensate. In other words, relativity is to spacetime what fluid dynamics is to water, useful, accurate, but not fundamental. Where did this model come from? Giorgio Volovic has one version. He says that spacetime might come from a fermionic quantum vacuum, like the ones found in superfluid helium-3. Topological invariants, which are deep mathematical properties of the void, tell us what kinds of objects and forces can form in this view. The speed of light is not a fixed value in these models. Instead, it is a feature of how the cloud behaves at a certain energy level. It could change at very high energies or in the early universe, which could help solve cosmic questions like the horizon problem without using inflation. What's more, this model offers a new take on dark energy. Instead of a mysterious cosmological constant, the accelerated expansion of the universe might result from quantum pressure in the superfluid, a kind of vacuum tension pulling space outward. There's also an interesting link to quantum chaos. When energy is added to superfluid helium, it can make spinning swirls and chaotic eddies. If our vacuum acts the same way, then the early universe might have been full of quantum turbulence, which are rapid changes that helped galaxies and the structure of the universe form. But how could we check this? That's the tough part. Gravity vacuum condensate models suggest small changes from the theory of general relativity. These changes could be in the way gravity waves travel or the way light bends near heavy objects. Some people think that new devices, such as LISA, the Laser Interferometer Space Antenna, will be able to see these changes. Others suggest that neutron star mergers or pulsar timing arrays might reveal signs of the vacuum's internal structure, echoes, delays, or interference patterns that deviate from standard predictions. Of course, there are risks. Does the fact that space is a superfluid mean that it can freeze, boil, or even get flaws? Could geometric problems in the vacuum spread like faults in the universe? Could a change in phase in the vacuum wipe out parts of the universe? This isn't a fringe idea, no matter how crazy it sounds. It adds to what we already know about physics and connects quantum mechanics, condensed matter, and astronomy. Geons, self-contained gravitational packets. What if gravity could twist itself into a knot that could hold itself together? What if that knot was made of nothing but space-time curve instead of matter? There are no atoms or fields. There is only gravity wrapping around itself. That's what geons, which stand for gravitational electromagnetic entities, are all about. Physicist John Wheeler came up with the idea for them in the 1950s. A geon would be a group of gravity, or electromagnetic waves, that are stuck in one place by their own warp. It would be like a tiny echo of spacetime shaping itself. The key idea: Einstein's equations allow for solutions where curvature energy binds itself. In typical mass-induced gravity, matter creates the curvature. But in a geon, the curvature is the matter. A geon could, hypothetically, orbit itself or oscillate, held together by the very geometry it creates. In Wheeler's words, mass without mass. There are two main types: gravitational geons, consisting of gravitational waves trapped in a toroidal loop, and electromagnetic geons, where electromagnetic fields and their energy curl into a similar confinement. Both would be balls of light or gravity, with no physical substance beyond the waves. Their existence relies entirely on general relativity's non-linear nature, allowing waves in spacetime to influence other waves, like ripples in a pond bending the paths of other ripples. So could they really exist? That's the big question. It can be hard to find exact, stable geon answers. A lot of the early models either fell apart or let energy leak out, spreading away instead of staying put. Later, better mathematical structures showed that quasi-stable geons could stay in place for very long periods of time in some situations, such as in anti-de Sitter space, or with certain boundary constraints. What would geons look like if they are real? How could we find them? They'd be dark, no atoms, no light emission, but they could produce gravity. A geon might mimic a black hole's gravitational pull, but without an event horizon. In theory, if you orbit one, you'd feel its gravity, but if you fell into it, you wouldn't hit a singularity. Instead, you'd pass through a region of intense wave interference, a storm of gravitational or electromagnetic oscillation. Astronomers would need to spot unseen mass in a region without the signatures of matter. Stellar orbit anomalies could point to geon-like objects. Ultra-compact, low-energy gravitational wave emissions, repeating patterns not tied to black holes, might signal geon echoes. Or, hypothetically, flashes of trapped light escaping if a geon decays. Geons blur the line between fields and particles. They suggest a universe where objects aren't always material. They can be pure geometry. They raise questions. Could geons be dark matter candidates? Could they seed galaxy formation? Or could they exist at microscopic scales, forming a hidden layer beneath normal matter? There's also a conceptual payoff. Geons show that gravity is more creative than just curving space. It can sculpt itself into knots, dance loops, form objects out of emptiness. It challenges our idea of what constitutes substance. In some quantum gravity approaches, researchers explore whether geon-like configurations could underlie other phenomena, black hole microstates, quantum solitons, or zero-point geon foam. But geons are still just guesses. No observations back them up, and if they didn't have quantum stability, they might only be in calculations and not in the real world. Still, the thought remains in gravitational physics like a ghost, a whisper of mathematics that can hold itself together. Geons are very interesting because they connect to bigger ideas in this exploration. Gravity changes reality, but in the right circumstances, it can also shape itself. In the deepest parts of the universe, space-time might put together problems of its own making and hide things that are made out of nothing but have meaning. The holographic principle. Is the 3D world a projection? What if the universe you live in, every star, every planet, every person you've ever met, is actually a projection? Not inside your head, but encoded on a distant boundary. That's the audacious claim of the holographic principle, a concept that flips our perception of reality. Instead of a three-dimensional interior governed by laws, it suggests that all of reality could be described by information encoded on a two-dimensional surface, just like a hologram. This idea originates from black hole thermodynamics. In the 1970s, physicists Jacob Bekenstein and Stephen Hawking discovered that the entropy of a black hole, a measure of its information capacity, is proportional not to its volume, but to the area of its event horizon. In other words, a black hole's information content scales with its surface area, not the region it encloses. That was staggering. It suggested that, fundamentally, physics in a region depends on what's written on its boundary. Gerard 't Hooft and Leonard Susskind extended this insight into a bold conjecture. Maybe the universe itself works this way. That information about everything inside a volume is encoded on its boundary. If true, what we experience as three-dimensional reality is a manifestation, a projection of deeper two-dimensional data. First, consider dimensionality. In holographic dualities, there can be a higher dimensional bulk world with gravity, curved space-time, black holes, and a lower dimensional boundary world without gravity, simpler physics, but containing the full information needed to describe the bulk. You can translate between them, like dual images in a stereo pair. The most concrete example is the ADES-CFT correspondence, formulated by Juan Maldacena in 1997. It equates a type of gravity in a five-dimensional anti-de Sitter (ADS) space with a quantum field theory on its four-dimensional boundary, conformal field theory or CFT. The physics of black holes, strings, and curved spacetime in the bulk corresponds exactly to the behavior of particles and fields on the boundary. Two completely different perspectives, yet mathematically identical. Gravity in the bulk emerges from quantum field theory on the boundary. The dimension we experience might be just a convenient illusion, an emergent phenomenon. If the holographic principle holds more generally, it could resolve paradoxes like the black hole information paradox by showing that information is never lost. It's always stored at the boundary and can, in principle, be retrieved by decoding the hologram. Some argue that even our universe, expanding, accelerating, seemingly de Sitter-like, could obey a holographic law. Maybe our 3D world is lagging behind a 2D frontier, encoded on visible or cosmic boundaries we haven't recognized yet. Why does this matter? Because it changes the way we think about reality. We might ask what the border of a volume looks like instead of what the inside of it looks like. It's possible that gravity and space are not basic, but rather emerging, coming from patterns of information on surfaces with less dimension. This could bring together quantum physics and gravity, but not by combining them into a single set of equations. Instead, it could show that what we call gravity comes from quantum interaction and information that is spread out on surfaces. Researchers are already exploring this. In labs, they simulate holographic systems using ultra-cold atoms or condensed matter systems. They test how entanglement patterns can mimic curved spaces or replicate gravity-like behavior. They study tensor network models, emergent geometries built from information links mirroring holographic duality. They also look at cosmology. Could the cosmic microwave background, light from the early universe, be a faint echo of holographic encoding? Or could cosmological boundaries at the edge of space hide deep information about dark energy, inflation, or matter? If the holographic principle is more than a mathematical tool, it means that everything is encoded on something else. The universe becomes less about objects in space and more about information patterns on surfaces. Black holes, stars, planets, they're all emergent. That flips reality on its head. Matter isn't the base, it's the shadow cast by information. Geometry, gravity, motion, all arise as projections from fundamental bits far removed from our perception. Do we live in an image in space? Maybe. It could be a metaphor, but the concept gives us a new way to look at things. It says that space, time, and gravity might not be real things at all. They might be records, sets of data. On the walls of space are stories. What about the walls? They could be anywhere and everywhere, just below the top of things as they are. Topology change. Can the shape of space rip and reconnect? Most of the time, we think of spacetime as a smooth, continuous sheet that bends, stretches, and maybe even warps because of gravity, but is always whole. What if, though, that's just a useful illusion? What if space can tear deep inside the quantum veil? This is the realm of topology change, the idea that the very shape of spacetime might not be fixed. In certain extreme conditions, like those found at the heart of black holes or the earliest instance after the Big Bang, the fabric of reality could undergo radical transformations. Holes could form, loops could snap or fuse, entire chunks of the universe might disappear or branch into new ones. Space might not just curve, it might mutate. Let's go back to geometry to get a handle on this. Topology is not about size or angles in math, it's about shape. This means that a coffee mug and a donut are the same because they both have one hole. So topological changes are big changes in the structure of a place, like ripping open a donut and putting it back together as a sphere. Applied to the cosmos, a topology change means a transition from one global structure to another. A space that was simply connected, no holes, might gain a handle. A separate region might bud off like a bubble or tunnel into another. In essence, the continuity of reality itself might be breakable under extreme conditions. But does science allow this? That's the hard part. Einstein's great theory of gravity, general relativity, is known for being very rigid when it comes to topology. Its equations work best on smooth surfaces that don't change shape. By adding a tear, or topology change, as scientists call it, you can get singularities, places where the math doesn't work, or places where causality is broken. Still, there are holes. It was proven by Stephen Hawking and Robert Geroch in 1967 that in classical general relativity, smooth shape change is not possible under certain energy circumstances. What about quantum gravity? That is a completely different animal. In quantum gravity models, especially in path integral formulations, all possible configurations of spacetime are considered. That includes those with different topologies. In fact, in quantum cosmology, the birth of the universe itself might be described as a topology change, a transition from nothing, no classical space, to something, a universe. In this view, topology is dynamic, not fixed. The wormhole is one of the most well-known thoughts about how topologies can change. A wormhole is a tube in spacetime that links two different places. Space has to change its shape and join in a new way for this kind of system to come together. In some types, this needs strange stuff to keep the throat open. In some, especially those connected to quantum foam, tiny wormholes on the Planck scale may constantly appear and disappear, making a sea of micro-topology change. Another related idea is the baby universe. According to some speculative theories, violent events like black hole formation might cause regions of space to pinch off, creating entirely new universes disconnected from our own. From our side, it's just a singularity. But from the other side, a cosmic birth. How would we know if there is a change in the topology? It's not clear. Changing the world framework of space is hard to see with the naked eye, but some signs, like complex cause structures, repeated patterns in the cosmic microwave background, or strange gravitational lensing events, might point to more than just curvature. They might point to changes in how space is connected. Quantum computers and systems for condensed matter have started to simulate changes in topology in the lab, which is even more interesting. Scientists can use these analog models to make places where particles appear and disappear when the underlying structure changes. These tests might help us figure out how changes in structure might happen in the real world. Topology change. Can the shape of space rip and reconnect? Space is like a medium to us. It's open and can be used in many ways, but it's still whole. Einstein's equations show that the background can bend and stretch because of gravity, but it has to be smooth all the time, always whole. What if, though, that thought is just a comfortable lie? It's possible that space-time isn't a single thing, but can tear, split, rejoin, and even create whole new branches of reality. This isn't sci-fi speculation. It's a serious possibility at the bleeding edge of theoretical physics. It's called topology change, and it challenges everything we thought we knew about how space behaves. In mathematics, topology is the study of properties that remain unchanged under smooth deformations. If you take a coffee mug and gradually stretch it into the shape of a donut, that's still the same topology, because both have one hole. But if you rip the mug's handle off, or punch a second hole into the donut, that's a topology change. Something fundamental about the object's shape has altered. Now take that logic and apply it to spacetime. General relativity allows for dynamic curvature. Gravity stretches and warps the fabric of the cosmos. But it assumes that the underlying topology stays fixed. No holes ripped open, no new edges sewn on. The geometry can flex, but the skeleton remains the same. That idea might not be true at the quantum level. Einstein's theory of relativity and quantum physics meet in quantum gravity, which says that spacetime is not a smooth line, but a changing web of possible outcomes. The structure of the world isn't set at this level. It could bubble, split, join back together, or even pinch off into whole new worlds. Imagine two separate areas of space that suddenly join with each other because of a change. This could be a bridge or a tunnel. That's not just a new shape, it's also a new direction. Or think of a single world that, when the energy level gets too high, splits into many separate areas that don't interact with each other and evolve on their own according to their own set of rules. That's not a dream, it's math. In classical general relativity, these scenarios tend to be forbidden. Changing topology often implies singularities, infinite curvature, or violations of energy conservation. The universe would have to pay a heavy price, physically and mathematically, to pull off a topological shift. But in quantum models, where space itself flickers and shifts on tiny scales, the rules change. Causal dynamical triangulations, CDT, is a strong structure. CDT doesn't model spacetime as a smooth surface. Instead, it does so as a stack of small geometric shapes, such as triangles and tetrahedra. As time goes on, these blocks can join in different ways to make new shapes. The models that were made show that spacetime could change over time like an organism, growing new areas or joining old ones together. It's folding in spacetime. Then there's the idea of vacuum tunneling. In some cosmological theories, especially those involving the multiverse, our universe is just one of many energy states, or vacua. These vacua can tunnel into one another via quantum fluctuations. When such a transition occurs, a new bubble of space with different laws and different topology can form and expand, pinching off from the original universe. This is called false vacuum decay, and if it happened once, it could happen again, right now. Somewhere in the far reaches of space, a new topological bubble could be forming, ready to devour or disconnect from our own. An interesting fact about this is that shape change might not be uncommon. It might even be necessary. Think about the Big Bang. At the start of time, the universe may have come from a topological shift, which means that an older structure broke or changed shape. It's possible that our space was formed when another structure collapsed, like an egg cracking open in space. It's possible for this process to repeat itself, with topologies dying and new ones being born, and universes giving birth to more universes. Could black holes be the seeds of new topologies? If matter collapses into a singularity, does it tear through the fabric of our universe and create a bridge to another one? Could wormholes, theoretical tunnels connecting distant parts of space, be evidence of topology change in action? Could consciousness, dark matter, or even the arrow of time be influenced by unseen topological features in the fabric of space? These aren't just what-ifs, they're active lines of questioning in modern physics, because if topology is mutable, then everything else might be too. Of course, this brings up a whole new set of problems. One is cause and effect. Do timelines get jumbled if space breaks and then heals? Your future self might be on the other side of a topological fold. Could you meet them? Could there be two versions of you in different post-transition boxes that don't know about each other? Conservation rules are another thing. During a structure change, does energy stay the same? Or does some of it get lost when space is changed? In traditional physics, these kinds of changes would need strange matter or situations that aren't possible. But quantum physics is about chances, not sure things. Even if there is a very small chance that the structure will change, it can still happen. Some theorists argue these transformations are surgically forbidden, meaning there are deep constraints that prevent spacetime from behaving this way. but others believe those constraints only apply to smooth, classical spacetimes, and that quantum geometry ignores them altogether. There's also the issue of continuity. If space tears, what happens to the fields and particles defined within it? Do they get cut off, duplicated, or reinterpreted in the new topology? These are open questions, and they strike at the heart of what it means for physics to be consistent. Some researchers believe topology change might not just be allowed, it might be the default behavior at the smallest scales. That at the Planck level, space-time is constantly flickering through topological states, and we only perceive a smooth universe because those transitions average out on large scales. In that view, our cosmos isn't a fixed entity. It's a breathing, shifting shape, constantly exploring new configurations, like a multi-dimensional jellyfish made of probability. What do we think about all of this? We now have a picture of reality that is much less static, rigid, and clear-cut than the ones we had as kids. A world that doesn't just bend, but breaks, reshapes, and starts over from the ground up. Asymptotic silence, where space becomes quiet near the Big Bang. The Big Bang makes us think of chaos, a white-hot oven with an endless amount of noise and density. But what if, strangely enough, the room gets quieter as you get closer to the beginning? Asymptotic silence is a possible state in which, close to the beginning of time, different parts of the world become so cut off from each other that they stop talking to each other. In this strange domain, space-time becomes so sharply curved, so rapidly evolving, that light itself can't keep up. The distance that light can travel shrinks faster than time can progress. The result? The causal connections, the conversations between regions of space, break down. Think about being locked in a room where the walls are moving so fast that your voice can't reach them. It's called asymptotic quiet. Some versions of BKL, Belinsky, Kolotnikov-Lifshitz, behavior talk about how we get close to cosmic singularities and include this idea. The BKL model says that the universe breaks up into causally separate regions near a spacetime singularity, like the one thought to have happened at the Big Bang. Each region does its own thing and spirals into its own chaos geometry. But here's the twist. Despite that chaos, the universe becomes silent. Points stop influencing each other. Space, as a connected fabric, shuts off. Time flows, but space stalls. This silence isn't absolute nothingness. It's more like an information blackout. And that could be important, because it means that before the classical Big Bang, before inflation, before photons started scattering, there may have been a phase where the geometry of space decoupled entirely. Some scientists think that this asymptotic silence phase could help them figure out the horizon problem. The horizon problem is the mystery of how different parts of the universe look so much alike, even though they are too far apart to have ever interacted. If early space was quiet, it might not need to talk to get in sync. It's possible that its rules were stuck in place, but they were still in line. Some people think this phase might hold information about the science before the Big Bang. It's possible that the early universe didn't start out as a fireball, but rather from a non-local quiet environment where geometry didn't start to come together until time did. Could this mean the Big Bang wasn't really the start, but rather a transition out of silence? Maybe there was structure, hidden, unordered, waiting to unfold. Asymptotic silence could act like a cosmic boot-up screen, a moment where the system loads, but nothing's running yet. In loop quantum gravity, this concept appears as a limit, where the spatial metric becomes degenerate. In string theory, similar ideas pop up when considering branes with zero separation. In causal set theory, the earliest atoms of spacetime might be so sparsely linked that no chain of events can traverse them. Black hole Planck cause. What lies beyond the singularity? There should be a point at the end of a black hole. A singularity is a knot in spacetime that is so thick that the rules of physics don't work and the knot will never end. But scientists don't like infinities. Our math stopped working when we see an infinity sign. They're alerts, warning signs. Because of this, a lot of experts think the singularity is just a dream, a place to start. The center of a black hole is home to that other thing, a limited thing, something real. A Planck core is what it's called. To understand the idea, we have to remember the scales involved. At the center of a black hole, gravity becomes extreme. General relativity predicts the collapse of matter into an infinitely small point. But that's because general relativity doesn't play well with quantum mechanics. It assumes spacetime is smooth and continuous. But quantum theory tells us zoom in far enough, down to the Planck scale, about 1.6 times 10 to the negative 35 meters, and space itself becomes foamy, jittery, and unpredictable. Right now, this is where quantum gravity comes in. Also, spacetime can't collapse to a true point in many models of quantum gravity, such as loop quantum gravity and some string-theoretic methods. Before everything falls apart completely, there is a quantum resistance that sets in. It's like spacetime pressure. Stopping the tightening is done. It makes it bounce. As a result, there is a place called the Planck core where matter is squished to Planck densities, but not to infinity. It's unbelievably dense, denser than anything else we can see in the universe, but it's still limited. This strange object is inside the event horizon, where light and information can't reach it. There is no point. It's not a hole. It's a part of space that is stuck in quantum chaos. So what's in there? Some ideas suggest the Planck core could contain fuzzballs, string-theoretic configurations of mass and geometry, replacing the classical point. Others propose it might be a remnant, a leftover stable structure from quantum collapse. In some models, the Planck core might even be connected to a white hole, a reverse black hole spitting matter out elsewhere, maybe even in a different universe. Loop quantum gravity in particular gives a vivid picture. Instead of a singularity, it predicts a quantum bounce. The collapsing matter reaches a minimum volume, then rebounds, creating a new expanding region of spacetime. If true, this could mean that every black hole births a new universe. Yes, that is true. It's possible that our universe or others could have formed from the Planck core of a black hole in a different universe. There is only the membrane at the singularity, the back door. And below that is a seed of new space-time that is wrapped in the old. Though these thoughts are still just guesses, they're becoming more popular. Hawking radiation, black hole chaos, and the firewall paradox are all signs that deep inside a quantum world needs to be fixed. Also, if those changes stop a real singularity, then the Planck core isn't just a theory, it's a look into a time before reality. We can't observe it directly. Nothing escapes the event horizon, but gravitational waves might carry hints. The very pattern of a black hole's collapse, its ring down, could whisper clues about what lies inside. Some physicists are already looking for subtle echoes in gravitational wave data, ripples from the collapse that don't match what a clean singularity would produce. And there are implications beyond black holes. If the universe once passed through a Planck core, if the Big Bang was itself a bounce, then studying these dense interiors could tell us about our own origin, about the moment before time, if such a thing exists. Anisotropic spacetime. Is reality directionally biased at small scales? What if the room isn't the same everywhere? It sounds like a simple plan. It's even clear. We know what left and right and up and down mean. Modern physics, on the other hand, says that on a big scale, the structure of spacetime is isotropic. In other words, it acts the same way no matter which way you look. The world doesn't have a favorite direction. Gravity pulls the same amount in all directions. Light always moves at the same speed. But zoom in close, deep into the quantum world, and this symmetry might break. The theory is called anisotropic spacetime, and it suggests that at incredibly small scales, far below what we can observe with today's technology, space and time might have preferred directions, like grooves in wood grain, like currents in a fluid. The smooth cosmic background we experience could be riding atop something subtly directional. In some versions of quantum gravity, anisotropy is built in. For example, in Horava-Lifshitz gravity, time and space are treated differently at high energies. Time has a distinct scaling behavior from spatial dimensions, breaking the symmetry between them. This leads to modified dispersion relations, meaning that at high energies, particles might move or interact differently depending on which way they travel. Even string theory leaves the door open. Compactified dimensions might curl differently in different directions. And if extra dimensions aren't perfectly symmetrical, their influence could imprint directionality into our observable 3D space. This isn't just theory. Some experimental hints have sparked interest. Observations of cosmic rays and gamma-ray bursts have been analyzed for signs of Lorentz invariance violation, tiny deviations that would signal a break in the symmetry of spacetime. So far, results are inconclusive, but the margins are shrinking. If anisotropy exists, it's subtle, but real. The early world is one of the most interesting points of view. At the very beginning of the Big Bang, when energy levels were close to the Planck scale, tiny anisotropies might have formed. These could be stuck in the cosmic microwave background, which is the faint glow from the beginning of the universe. Some experts think that some strange patterns in the CMB, like the so-called axis of evil, show that the universe is moving in a certain way. If true, anisotropic spacetime would force a rethink of physics. Many foundational principles like Lorentz symmetry and the constancy of the speed of light depend on isotropy. Break that symmetry and the standard model starts to crack. That could be a good thing though. The rules must change at the Planck scale. Changes in quantum mechanics bend spacetime in strange ways. If direction is important, if space has a direction, then particles might not just move through space, they can move with or against the grain. In some areas, the signal might spread more quickly. Some people might not want to move. Gravity could change how it curves. Time might not be running smoothly. Some even speculate that this could help unify gravity with quantum mechanics. By introducing a tiny directional asymmetry, we gain a new variable, one that could plug into equations that don't otherwise mesh, like a hidden key buried in the grain of the cosmos. Stochastic gravity, a noisy, flickering background below order. A smooth, quiet curve is what we like to think of as gravity. It bends spacetime into circles around planets and keeps galaxies moving. But what if gravity is loud below that beautiful surface? This is stochastic gravity, a theory that says spacetime might flash with random quantum changes. Imagine a trampoline that not only sags under a bowling ball, but also shakes so little that it looks like it's living with tiny movements. There is a hum in the background of this sound. There is chaos just below the order. In Einstein's general relativity, gravity is elegant, deterministic. A massive object curves the geometry of space, and smaller objects follow those curves. But this classical picture starts to break down when you mix it with quantum mechanics. In quantum field theory, particles are just excitations in underlying fields, and those fields constantly fluctuate, even in what we call empty space. Now apply this to gravity. If spacetime is a quantum entity, it too must fluctuate. But gravity interacts with everything. It responds to the energy and momentum of particles. So, if those particles are jittering due to quantum fluctuations, gravity should respond. These are stress energy fluctuations, the heartbeat of quantum matter fields, randomly affecting spacetime. Stochastic gravity tries to bridge this gap. Instead of assuming gravity always follows neat equations, it says, what if there's an extra term? A noise term. One that captures the random quantum agitation of matter fields acting back on spacetime. This back reaction is tiny under normal conditions. But in the early universe, during black hole evaporation or near Planck scale densities, it could be everything. You can think of it like this. Imagine a pond with a big stone in the middle. Normally you throw in a pebble and see ripples, but if the pond is already disturbed, filled with micro ripples from other drops, you can't easily trace which ripple came from which cause. The surface becomes stochastic, random. You need new tools to study the pattern beneath the noise. Stochastic gravity gives us those tools. It introduces something called the Einstein-Langevin equation, a version of Einstein's equations infused with randomness. It allows researchers to calculate not just the average behavior of spacetime, but the fluctuations around that average. Why does this matter? Because the universe isn't perfectly smooth. It has structure, galaxies, voids, fluctuations in the cosmic microwave background, and those seeds of structure may have come from quantum noise amplified by gravity. Stochastic gravity could help explain how microscopic uncertainty became macroscopic order. And black holes? This theory offers a possible window into the information paradox. If the evaporation of a black hole is influenced by random quantum feedback, then perhaps the information isn't lost, it's encoded in the flicker. In an even stranger twist, stochastic gravity could say that space is never really still. Spacetime might shimmer with quantum static even in the emptiest space. In the future, instruments that are delicate enough to record the tiniest gravitational waves or quantum memory effects might be able to pick up on this gravitational noise flaw. Disordered locality, when nearby points aren't actually near. When used in everyday language, the word near means something clear. A chair next to a desk, with a friend next to you. There are two dots on the page. We assume that if two things look like they are next to each other, they actually are, in every way, physically, spatially, and causally. But when you scale reality down to the Planck scale, which is about 1.6 x 10 circumflex 10 to the negative 35.5 meters, this natural sense of closeness goes away. The strange and disturbing world of disordered neighborhoods is now open to us. This idea turns the basic way we think about space on its head. It seems to say that closeness is not essential. Those things that seem close may actually be very far away in the vastness of space. And things that seem far away might be connected beneath the geometric fiction we call space. Maps can help you understand this. The Mercator model, which is often used in schools, shows that Greenland is bigger than Africa. That's not true, though. Africa is bigger than Greenland by more than 14 times. The map isn't telling us the truth because it's trying to make a sphere look like a flat surface. Now picture this same kind of error coming from the fabric of space itself, not from maps. In classical physics, the universe is a smooth continuum. Space and time are part of a unified field called spacetime. Objects influence each other locally. Gravity acts across space. Light travels along straight lines, and fields propagate through adjacent regions. Locality reigns supreme. But quantum gravity, the elusive theory that seeks to unify general relativity and quantum mechanics, tells a different story. It proposes that spacetime is not a backdrop, but an emergent phenomenon, a stage built from something else, perhaps entangled information, discrete geometric elements, or a quantum network. If that's true, then the idea of nearness becomes suspect. Enter loop quantum gravity and causal set theory. In these approaches, spacetime is built from discrete units like pixels on a screen or nodes in a network. These units connect through quantum relationships, not physical coordinates. It's not about measuring distance with a ruler. It's about tracing connections through an invisible web of links. Imagine 3 points, A, B, and C. In classical space, A might be next to B and B next to C. So we'd expect A and C to be nearby. But in a quantum graph, A might be connected to C directly, while B is part of a different branch entirely. Proximity becomes a matter of graph structure, not physical location. This leads to disordered locality, a framework in which the geometry we see is a projection, possibly a flawed one, of a deeper, non-local structure. It's like looking at a tangled mess of wires from above and assuming that segments lying close together are connected. In truth, they might belong to opposite ends of the system. What's the big deal? Because proximity is one of the most basic ideas in physics. Almost all major theories, from electricity to quantum field theory, believe that particles interact with each other nearby. That is, they only have an effect on things close by. This assumption falls apart, though, if disordered location is real. What we think of as local interactions could actually be non-local processes that are acting like local ones. Quantum coupling is one of the best ways to see this. Particles that are entangled can change the state of each other instantly, no matter how far apart they are. It was what Einstein called spooky action at a distance. What if this isn't movement from far away, though? In a secret layer of spacetime, what if entangled particles are already linked? What if they are closer than they seem? The ER equals sign EPR conjecture takes this idea further. Proposed by Leonard Susskind and Juan Maldacena, it suggests that every entangled pair of particles is connected by a tiny wormhole, a microscopic bridge through space-time. The ER stands for Einstein-Rosen bridges, wormholes, and EPR refers to Einstein-Podolsky-Rosen entanglement. This has very big effects. It might help us understand how information gets out of black holes without breaking the rules of quantum physics. At long range, it could show how teleportation works. It could also solve the horizon problem, which is the mystery of why areas of the world that are very far away look so much alike, even though they shouldn't have had time to meet. It would make sense if they were linked below the ground. It's hard to test random locality because we can't directly see anything at the Planck size right now. But there may be hints that aren't clear. Scientists could look for strange patterns in particle collisions with a lot of energy, signs that Lorentz symmetry has been broken, or weird paths in scattering tests. These paths could point to non-local jumps or hidden space shortcuts. Some researchers are exploring this through simulations. In certain condensed matter systems, geometry emerges not from position, but from quantum entanglement patterns. These models can behave like toy universes, allowing us to explore what it would feel like if locality were broken or disordered. It's like building a sandbox version of the cosmos to test ideas we can't yet observe directly. We've always relied on our senses to interpret space. Our eyes tell us what's near, our hands confirm it. But in a universe with disordered locality, these senses become irrelevant. You could be standing next to something in the visual sense, but be miles apart in the true quantum fabric, and something across the galaxy might be only a quantum heartbeat away. It's like a shell game in space. We're looking for shades of nearby things and thinking that projection is true. But this idea also makes a lot of sense when you think about how memories and dreams work. You can jump between scenes and places in your dreams. In memories, events that happened years apart can seem close. Our thoughts work in a way that isn't limited to one place. Maybe the universe does too. If disordered locality turns out to be real, it will reshape our understanding of what space is and what it isn't. It will tell us that the universe is not made of things in places, but of relationships in flux, that beneath every apparent structure lies a deeper, invisible logic. Causal dynamical triangulation, building spacetime from simplices. What if the universe isn't smooth and continuous? What if it's made up of tiny geometric blocks, like Lego pieces for the universe? Such an idea is at the heart of causal dynamical triangulation, or CDT. It is one of the bravest attempts to rebuild spacetime from scratch, and it all starts with a simple idea that seems complicated at first. Build everything out of triangles. CDT reimagines the fabric of the cosmos using tiny, flat building blocks called simplices. In 2 dimensions, that's a triangle. In 3, it's a tetrahedron. In 4 dimensions, where time is folded in, these become 4 simplices, the scaffolding of spacetime. This model doesn't assume a smooth, continuous geometry. Instead, it treats spacetime like a mosaic of flat chunks, dynamically connected in a way that obeys one crucial rule: causality must be preserved. Time must always move forward. No loops, no paradoxes. That's what sets CDT apart from other discrete spacetime theories. The universe is imagined as a sum over histories, a concept borrowed from quantum mechanics. In standard quantum theory, particles don't follow a single path. They take all possible paths, each with a certain probability. CDT applies this idea to spacetime itself. It considers all possible ways you could build a universe from these 4-dimensional blocks, and then calculates which configurations dominate based on how well they preserve causality and fit observed physics. When you run the simulations, you don't get chaos. You don't get a broken universe. You get a four-dimensional spacetime that, on large scales, looks exactly like our own. This is very important. Euclidean dynamical triangulation and many other methods to quantum gravity fail to explain anything like the universe we see. CDT, on the other hand, automatically returns to a de Sitter universe, which fits with the idea that the universe is expanding faster than usual. To sum up, why use simplices? Since they follow the rules of math, they give you a controlled way to figure out shape, volume, and connection. To understand gravity, you don't need smooth curves. Just watch how the shapes bend and stick together. The beauty of CDT is that it doesn't require you to assume a background spacetime. It builds space and time from scratch. It's a background-independent approach, meaning spacetime isn't a stage, it's an actor. It emerges from the dance of these discrete elements, and you can test it, at least in theory. At the Planck scale, which is about -10 to -35 meters, if CDT is right, spacetime should look rough and broken up. This might leave marks in the noise from gravitational waves, the behavior of high-energy cosmic rays, or the precise time of photons from gamma-ray bursts far away. Some physicists even speculate that CDT might eventually unify with other quantum gravity approaches, like loop quantum gravity or spin foam models. After all, if multiple roads lead to the same structure, we might be closing in on truth. Supertranslations. Hidden symmetries in the vacuum. We usually think of a featureless space when we think of a vacuum, which means pure, absolute nothing. A quiet void that doesn't have any shape, form, or behavior. But in the field of theoretical physics today, this couldn't be further from the truth. There is no such thing as empty space. It's full of tiny, unnoticeable structure. Supertranslations are a group of secret symmetries that are not in space itself, but on the edges of it. They are one of the most disturbing of these structures. To grasp this idea, let's rewind a bit and talk about symmetry in physics. Symmetry isn't just an aesthetic idea, it's a foundational principle in the laws of nature. A symmetry in physics means that certain transformations, like rotating, shifting, or scaling, leave the underlying laws unchanged. This is powerful. Conservation of energy comes from time symmetry. Conservation of momentum comes from spatial translation symmetry. In other words, symmetry represents order. And in physics, order often means law. When something is symmetric, it follows a predictable pattern, and those patterns are what we recognize as the laws of nature. So when symmetry breaks or behaves unexpectedly, it might signal a deeper shift in the structure of reality itself. Now, use your thoughts to the fullest. Expand all the way, past galaxies and quasars, to the edge of the universe that can be seen, and then even farther away. Think about where light rays end up if they never get swallowed or caught. They just fly off into the distance forever. Null infinity is the name for that place, which is vague but important. It's not a place in space. It's more of an idea of the edge of reality. Light has reached its end. In the 1960s, physicists working on Einstein's equations began probing this mysterious edge. They discovered something shocking. The vacuum, it turned out, has a symmetry group operating at null infinity. This group came to be known as the Bondi-Metzner-Sachs group, or BMS group for short. It includes the ordinary translations in time and space, basic shifts that move things around. But it also includes something stranger, something unexpected, something called supertranslations. Unlike normal translations, which move every point in space the same amount, supertranslations are direction dependent. They alter space-time not in a uniform way, but in a warped, angle-sensitive fashion. Imagine pulling on the corners of a rubber sheet, not equally, but more in some directions than others. That's the flavor of supertranslations. They act like tiny, invisible tides, nudging the vacuum itself in irregular ways. For decades, these exotic symmetries lived in the shadows of physics. Interesting to mathematicians, but considered more of a quirk than a clue. That is, until black holes entered the picture. Black holes are the ultimate testing ground for the laws of physics. They devour matter and information, crush spacetime into singularities, and evaporate over cosmic time via Hawking radiation. But this evaporation raises a terrifying question. Does information disappear forever? If it does, that would shatter quantum mechanics' most sacred principle, that information is never truly lost. Enter the soft hair hypothesis, a daring idea that could bridge the gap. Proposed by Stephen Hawking, Malcolm Perry, and Andrew Strominger, this idea suggests that black holes might possess supertranslation hair, subtle imprints left on the geometry of spacetime by everything that falls into them. These aren't visible hairs. They're not like ripples on water. They're ghostly, near-invisible disturbances encoded in the BMS symmetries at null infinity. These traits that look like hairs could keep data safe without breaking any known physics rules. The information could be written into the structure of spacetime at its edge instead of being stored inside the black hole, where it would be killed at the singularity. In this case, black holes don't get rid of information. Instead, they move it around in the strangest way possible. It's not just a black hole thing either. There is a strong link between these symmetries and soft theorems in quantum field theory. These theorems explain how soft particles, which are low-energy particles, behave when they are released or absorbed. Soft gravitons and soft photons interact with the vacuum in ways that leave lasting marks. Soft gravitons are thought to carry gravitational force. The expectations of supertranslations are right on the money with these clues. So, the vacuum isn't silent. It records whispers. When something happens, when matter collapses, when light flies by, when energy shifts, the vacuum keeps the memory. This is sometimes referred to as gravitational memory, and it might be observable. In gravitational wave astronomy, detectors like LIGO and Virgo have already captured the violent tremors of spacetime from colliding black holes and neutron stars. But some researchers believe that after the waves pass, they might leave behind permanent scars, small, lasting shifts in the shape of spacetime. These would be the experimental fingerprints of supertranslations, confirming that the void is not blank, but responsive, alive. This has very important effects. If supertranslations are real, not just in math, they tell us that space's vacuum is like a cosmic blackboard that is always being written on by everything that happens in the universe. It would mean that no event is missed. No conversation is ever really lost. These symmetries hint at a deep unity between gravity, quantum mechanics, and information theory. Supertranslations might be the missing piece that allows information to travel safely across the fabric of spacetime, from violent origins to calm horizons. They might reconcile quantum information with classical geometry. The scariest thing about them might be that they point to the idea that spacetime isn't the base of reality at all. If there are secret patterns in the vacuum, then those might be the real world. Geography might be a side effect. Maybe what we think of as reality is only the very tip of a more complex mathematical framework. Penrose, who helped formalize the BMS group, has long hinted that our understanding of space and time is incomplete. Supertranslations support that notion. They force us to accept that the universe has layers, not just in scale, but in meaning. What seems like nothing might contain the keys to everything. Even now, physicists are working to generalize these ideas. Could supertranslations apply not just to gravitational systems, but to electromagnetic ones? Could they connect to entanglement and holography? Could they help decode the true nature of the vacuum energy that drives cosmic expansion? No one knows yet, but the fact that we're even asking these questions tells you something. The void is lying to us. It looks quiet, but beneath the surface it's buzzing with order. Twistor theory. Reality made of light paths. What if there are no particles, points, or even spacetime at the deepest level of reality? It's possible that the world is made of light, and I'm not just using that as a metaphor. That's what Twistor theory is all about. Sir Roger Penrose, one of the smartest people in mathematical physics, came up with this innovative scheme in the 1960s. It says that the best way to explain everything, from particles and fields to the shape of space-time, is not with numbers and dimensions, but with the paths light takes, and how those paths connect to each other. In most physical theories, you start with space and time. You lay down a grid, 3 dimensions for space, 1 for time, and describe everything that happens within it, where particles move, how fields interact, when events occur. In this familiar setup, points in space-time are primary. They're the locations where things are. But Twistor theory flips this on its head. In the Twistor view, a single point in Twistor space represents an entire light ray in space-time. Rather than building physics from chunks of space, Twistor theory builds it from relationships between light rays, called null geodesics, in relativity. It's an attempt to rebuild the foundations of physics from a different angle, literally. It's a switch in viewpoint so radical that the very concept of time becomes a secondary artifact, not a starting point. In a sense, the theory removes the stage on which physics plays out and replaces it with a dance of angles, directions, and flows. Light rays aren't just how we see the world. They may be the threads from which the world is sewn. Twistor space isn't easy to picture. It lives in a higher dimensional complex geometry that doesn't map neatly onto our everyday understanding of space. But inside this mathematical structure, the behaviors of massless particles, like photons and gluons, turn out to be surprisingly simple. Problems in quantum field theory that normally take hundreds or even thousands of pages of calculations can be reduced to a few pages of elegant Twistor math. The practical success of this shift was proven in the early 2000s, when Edward Witten, the father of modern string theory, connected Twistor space to superstring theory. This was a breakthrough that revealed a new way to simplify the calculations of scattering amplitudes, the probabilities of various outcomes when particles collide. What once seemed impossibly complex became almost geometrical in nature, hinting that geometry, not equations, might be the truest language of particle interactions. This insight evolved into an even more mind-blowing construct, the amplituhedron. Think of it as a multidimensional geometric shape that encodes all possible particle interactions, without using space or time at all. In this model, events don't occur in space-time. Instead, they are the result of intersecting planes and surfaces in an abstract Twistor-like space. From this bizarre crystalline world of relationships, the illusion of space-time and everything that happens in it emerges. This changes the whole picture. We don't use space-time to figure out what particles will do. Instead, we build space-time by looking at how massless lines relate to each other. And the consequences are huge. There is no such thing as space-time if Twistor space is real. It's coming up. When you look at the network of light exchanges on a big scale, you can see the smooth, classical illusion. Conformal symmetry is an important mathematical idea in many basic theories, especially when energies are high. Twistor theory fits in perfectly with it. According to conformal symmetry, some physical rules don't change when the size of an image is changed. This means that the images look the same whether you zoom in or out. Twistor space is naturally conformal, which makes it a great way to describe the early universe, or the Planck scale foam below space-time. Then there's the problem of time, a huge stumbling block in theoretical physics. In quantum mechanics, time is a fixed background, a parameter that just ticks forward. In general relativity, time is part of the dynamic geometry, stretching and warping with gravity. Reconciling these two perspectives has been one of the major headaches in unifying physics. Twistor theory sidesteps this entirely. In Twistor space, time is not fundamental. It's reconstructed from how light paths intersect and diverge. You don't start with time, you build it from the geometry of light. This is especially powerful when thinking about quantum gravity, the long-sought theory that would combine quantum mechanics with general relativity. Twistor theory doesn't just offer new tools for this unification, it reframes the question. If space and time are emergent, then the quest for quantum gravity may not require us to quantize space-time itself, but rather to understand how networks of light interactions give rise to it. But it's not just numbers that make no sense. Twistor-based methods are now commonly used in high-energy physics. They are used in cutting-edge works on gauge theory and supersymmetry, as well as analyzing data from the Large Hadron Collider, LHC. They're changing the way scientists do calculations, see how things connect, and even what a particle is. What do these logical conclusions mean? They are amazing. If the world is made up of light lines instead of physical matter, then everything we think of as matter, force, or motion is just a shape in the geometry of light. The thought makes me think of old metaphors, like how light is truth, or how it is the body of God. On the other hand, Twistor theory says it's science, not art. There are some things that Twistor theory can't do. It does a great job with particles that don't have mass, but adding mass is still hard. It is still not fully possible to apply Twistor methods to gravity in a nonlinear way. Even though it is very well put together, Twistor theory is still just a set of mathematical tools and not a fully proven theory of nature. That doesn't make it less valuable, though. It just means we're just starting to understand how far it can reach. Some physicists believe that as our understanding of quantum information, holography, and entropy deepens, Twistor concepts will become increasingly central, not just as an alternative framework, but as the underlying code of the cosmos. Perhaps we are now only scratching the surface of a reality where coordinates are obsolete, clocks are illusions, and the entire universe is a network of shimmering, intersecting rays. Finally, what is below the surface of spacetime? Twistor theory says that it's not math, not even little bits, but light itself, with its complex dance moves that make everything we see, feel, and measure possible. If that's true, then physics is more than just the study of fields and forces. It looks at how things connect, how lines work, and how things move. At its core, reality may be a dance of light that we are still learning about. Emergent gravity. What if spacetime is a side effect? Think about getting into a game. You're walking through a world where you can feel the wind, see the sunrise, and hear sounds far away. Even though it all seems real, you know it's all just code, the result of more complex rules being played out on a computer screen. That's the provocative idea behind emergent gravity, the notion that spacetime and gravity aren't fundamental forces or structures, but side effects. They emerge from deeper hidden rules about information, entropy, and quantum mechanics. This concept gained major traction thanks to theoretical physicist Eric Verlinde. In 2011, he proposed that gravity isn't a force at all. Instead, it's an entropic phenomenon like heat spreading through a room or pressure rising in a compressed gas. According to this view, gravity arises because information wants to maximize entropy, and that drive causes matter to move the way it does. Here's an analogy. Picture a rubber sheet with marbles on it. The marbles roll toward each other because of the curvature in the sheet. This is the standard Einsteinian view of gravity. But in emergent gravity, the sheet itself is an illusion. What's really happening is that the system of marbles is trying to maximize information flow. The curvature is just how that looks in our macroscopic world. This turns everything around. Matter doesn't belong in space. Power and matter don't change places. Space and gravity are made up of tiny degrees of freedom, which are like bits of quantum information. Emergent gravity is based on holographic concepts, the physics of black holes, and the idea of quantum coupling. An important source of ideas for it is the Bekenstein-Hawking entropy formula, which showed that a black hole's entropy is related to its surface area rather than its volume. Yes, that is strange because it means the world keeps data on its edges instead of inside them. This ties directly to the holographic principle, the idea that everything happening in a 3D space can be described by a 2D theory at its boundary. If that's true, then gravity, and even the geometry of spacetime, are just reflections of deeper processes encoded elsewhere. Verlinde's model made headlines again in 2016 when he applied it to galactic motion. He showed that his version of emergent gravity could explain galaxy rotation curves without invoking dark matter. That was huge. While it hasn't replaced dark matter yet, it opened a new front in the fight to explain missing mass and energy. Some people disagree with emergent gravity, saying that it doesn't make any statements that can be tested and is instead just a recycling of ideas from statistical mechanics. But fans say that's exactly the point. We need to stop thinking about physics in terms of forces and start thinking about reality in terms of information. From this point of view, even space and time are just images held together by quantum bits. The world is like a quantum error-correcting code that keeps chaos and order in balance and keeps things running smoothly on unimaginable scales. In this framework, the Big Bang wasn't a literal explosion in space. It was the initialization of a massive data structure. Gravity is the way that structure tries to preserve itself. And black holes? They're information firewalls, repositories of lost coherence, where the rules we know begin to break down. This brings up a scary question. If gravity is emergent, what else is it? Are particles just shapes? Are fields really just changes in something deeper, like a quantum computing base? Could awareness, which is thought to be the final barrier, be a part of this new chain of events? There is one thing that is clear. If emergent gravity is true, we have only scratched the surface. It's possible that reality is just a small part of something much bigger. String net liquids, matter and space as a unified phase. Think about what would happen if the difference between particles and space wasn't like the difference between apples and air, but like the difference between ice and water, just two forms of the same material. That's the crazy but more and more likely idea behind string net liquids. It's an idea that could bring together not only matter and forces, but also space itself. Let's go back to get there. In the old way of thinking about physics, space is like a background, and particles are like things that move through it. Fields, which are changing things that fill all space, are added to quantum field theory. But even here, space and particles are dealt with separately. String net theory asks, what if they're not? It is not from string theory that the word string net comes from, even though the names sound alike. It was created by Xiaogang Wan and Michael Levin in the early 2000s while they were researching quantum spin liquids, which are strange states of matter in which electrons behave like spaghetti and can't line up like in a normal magnet. In a string net liquid, the vacuum, the true ground state of reality, is a dense, fluctuating network of strings. These strings aren't made of energy or matter in the usual sense. They are quantum excitations, entangled webs where nodes and links weave in and out of existence. Crucially, both particles and photons emerge as collective excitations of this network. If this is true, then particles like electrons aren't fundamental, they're ripples in the string net. And photons, those carriers of light, aren't fundamental either. They're just another pattern, another vibration. In this view, everything we see, touch, and experience is a pattern dancing on a deeper, invisible substrate. In simulations, researchers showed that both Fermi statistics, the rulebook for particles like electrons, and gauge interactions, the math behind forces like electromagnetism, emerge naturally from string net condensation. That means these foundational aspects of physics might not need to be built in. They just appear automatically if the strings are tangled the right way. So instead of asking what particle is this, we might someday ask, what configuration of the string net is this? And instead of asking, where is space, we'd be asking, what's the shape of the string net here? Wen even proposed that space itself is nothing more than a huge quantum entanglement pattern, a smooth illusion generated by the collective behavior of countless quantum bits arranged in string-like forms. This would explain why space appears continuous and smooth on large scales, but might be granular or even foamy if you zoom in far enough. Let's compare the two. Picture a distorted image. When you zoom in, it looks like a circle. When you zoom in, it's just a rough group of squares. Let's look at the smooth version of string net theory. On the inside, though, it's all digital and jumbled. It's shocking what this means. To begin, this theory says that string nets, which are a type of physical matter, might be the source of all particles, fields, and spacetime. We've never been brave enough to suggest such a deep level of unity. Second, it offers an answer to one of the biggest mysteries in physics: why our universe has both bosons, force carriers, and fermions, matter particles, and why they behave the way they do. If string-net condensation naturally produces both, we don't need to invent exotic symmetries or hidden particles to explain it. Third, it implies that quantum entanglement isn't just a spooky phenomenon, it's the engine of reality. If space, particles, and forces all arise from entangled patterns, then entanglement is more fundamental than geometry, mass, or even time. There are, of course, problems. String-net liquids have mostly been studied in 2D and 3D lattice models that are very simple. These models are often based on condensed matter systems. It is very hard to make these bigger enough to show how complicated our 4D spacetime really is. Also, unlike some ideas that can be tested, string-net models are still in the early stages of connecting with what we can see in the universe. Still, more and more people are starting to believe this, especially since quantum information theory is becoming more popular and entanglement is being seen as the real stuff that makes spacetime work. Holography and black hole chaos are just two examples of how quantum connections are deeply rooted and connect everything. If that's the case, then the vacuum isn't empty, it's full, just in a very quiet way. And everything we observe, from electrons to gravity to light, is just a ripple, a twist, a knot in that hidden sea. Fractal spacetime, smaller scales, greater complexity. You might think things get easier as you get closer to them. Less big pieces, structure is clearer, more simple rules. From cells to atoms to quarks, that's always been how cameras and physics have worked. However, what if that pattern ends one day? The universe might not get easier as you go deeper, but it might get stranger. Welcome to fractal spacetime, a radical idea suggesting that the fabric of the universe becomes more tangled, more irregular, and more dimensionally bizarre as you approach the Planck scale. Let's start with what a fractal is. In mathematics, a fractal is a shape that repeats its pattern at every scale. Think of a fern leaf, or a snowflake, or the edge of a coastline. Zoom in, and you see the same jagged complexity as before. There's no smooth core, no end to the detail. That's what makes fractals powerful and strange. Now apply that concept to spacetime itself. In a fractal universe, the closer you look, the more dimensionality changes. On everyday scales, we live in 3 dimensions of space and 1 of time. But zoom down to 10 to the minus 33 centimeters, right near the Planck length, and those dimensions might become non-integer values, like 2.7 or 1.9. This isn't just made-up numbers. It shows up in a number of separate methods to quantum gravity. For instance, causal dynamical triangulations, CDT, a method for putting together space-time from small geometric pieces, has shown that space acts like it has 2 dimensions at very small scales, even though it has 4 dimensions in the big world. Asymptotic safety and non-commutative geometry are 2 other models that hint at reducing the number of dimensions. As dimensions go down in these situations, the laws of physics become less free-flowing and more ordered. In a strange way, that could be the key to getting quantum gravity to work properly. Why would the universe behave like a fractal at its core? One reason is that smoothness is not natural in quantum systems. On tiny scales, energy fluctuates wildly. Fields jitter, distances blur. Trying to force a smooth geometry onto such a turbulent arena is like drawing a perfect line on boiling water. It doesn't stick. Fractals, on the other hand, thrive in chaos. Their self-similar, irregular structures are born from disorder. They can exist without smoothness. That's why some physicists think the ultimate description of the vacuum might be fractured, not flat. There's also the matter of facts. The Bekenstein bound, which says how much data can be kept in a certain area of space, points to behavior that doesn't change with size, which is exactly what fractals offer. If space is made up of separate bits, then its shape might easily follow fractal rules. Fractal spacetime might even be able to explain some strange things about the universe. On a big scale, the world might look flat, but the geometry below might be anything but flat. For example, the average height of ocean waves looks like a straight line from space, even though they're moving around a lot closer up. But this concept comes with big questions. How do we define a metric, a distance, on a fractal structure? How do you do calculus or physics in a space that isn't smooth? And how does time behave in a dimensionally unstable universe? These aren't just theoretical concerns. If the structure of spacetime is fractal-like, then our equations need an upgrade dot. We might need to replace continuous variables with fractional derivatives, a mathematical tool already used in some branches of physics, but rarely applied to the foundations of reality. Some researchers have tried using spectral dimension as a probe, measuring how particles diffuse in space. In fractal geometries, the diffusion behaves differently than in flat space, revealing the hidden complexity of the background. If in the future experiments, maybe using very high-energy cosmic rays or exact studies of black holes, find strange things that match fractal behavior, it could start a new era in physics. One day, the dream is to be able to zoom in on the universe and see its fractal structure, which would be like an MRI of space-time. But the theory still has a greater meaning. It reminds us not to expect things to be simple on the outside. It's not just a pretty thought that nature gets more complicated as you go deeper. It could be a law of physics. We might not find straight lines and flat surfaces as we get closer to the Planck scale. Instead, we might find endless loops of structure that split and twist forever. Non-local hidden variables, beneath the quantum curtain. Something strange about quantum physics. Every time you hear the truth, it doesn't feel right. Particles are waves. Cats can be both dead and living, and seeing something changes it. Things that happen in one place can quickly change things in another place, even if that other place is light years away. This is called not being local. What do the results mean? These go beyond what you learn in physics class. They make us think there's something deeper going on, a layer of reality we haven't fully understood. In the 1930s, Albert Einstein, along with Boris Podolsky and Nathan Rosen, published the now famous EPR paradox. They argued that quantum mechanics couldn't be a complete theory because it allowed for what Einstein called spooky action at a distance. If two particles become entangled, a measurement on one instantly determines the state of the other, no matter how far apart they are. This violated Einstein's view that information can't travel faster than the speed of light. Their solution? There must be hidden variables, extra pieces of information embedded in particles from the start that determine outcomes but are hidden from us. These variables would restore determinism and eliminate spooky behavior. It was elegant, clean, and wrong. Enter John Bell in the 1960s. He developed a testable inequality, now called Bell's theorem, that could distinguish between quantum mechanics and any theory with local hidden variables. Experiments since the 1970s, and especially in the last 2 decades, have violated Bell's inequality again and again, proving that local hidden variable theories can't explain quantum behavior. So, are factors that are hidden dead? Not quite. Non-local secret variables are still a place where they could hide. In this view, particles carry extra information, but that information is linked over very long lengths, beyond what we think of as space. It's not just science fiction either. Bohmian physics, which is one of the most well-known ways to understand quantum physics, uses this very idea. In Bohmian mechanics, particles always have definite positions and velocities, but they're guided by a pilot wave that evolves according to the Schrödinger equation. This wave isn't confined to the particle. It spreads through space, interacting with other waves, and encodes non-local information. Two particles entangled in Bohmian theory are connected through this underlying wave, and it's the wave, not faster than light signals, that coordinates their behavior. This means the universe has a hidden layer, a non-local substrate, where information is shared instantly. From our point of view inside spacetime, it looks like magic, but in the deeper geometry, it's just how things are wired. Even stranger is the idea that this secret layer may not only affect particles, but it may also be what makes spacetime possible in the first place. In some emerging theories of space and time, the shape we see is just a fiction held together by quantum entanglement. In a network, 2 points in space may be close, even if they are very far apart in 3 dimensions. How can we find out more about this secret world? Quantum teleportation is one way this could work. Entanglement and regular communication are used to send information about a quantum state in these studies. It doesn't break the law of causality, but it does show that non-local relationships are real and work. Quantum gravity is another new area of study. Some ideas, like the ER=sin EPR theory put forward by Juan Maldacena and Leonard Susskind, say that wormholes and entanglement are like 2 sides of the same coin. From this point of view, quantum links, which are relationships that go beyond space, might be what holds reality together. Yet despite the elegance of these ideas, we face enormous challenges. Non-local hidden variable theories often require an absolute frame of reference, which seems to go against relativity. They also risk becoming underdetermined, meaning they can explain anything but predict nothing. Physics, after all, demands testable consequences. Still, we might be inching closer. Bell test experiments are becoming more sophisticated, closing loopholes that critics once used to question their results. New tools like quantum networks, entanglement swapping, and delayed choice setups are pushing the boundaries of what we can observe. Torsion fields, the twisting side of gravity. The story is well known to most of us. Newton said that gravity is a force between things. Einstein turned things on their heads by showing that gravity is actually the curve of space-time, which bends like a spring when a bowling ball hits it. It was a big deal. What if that beautiful curve isn't the whole picture, though? It's possible for space-time to twist instead of just bend. We're now entering the less well-known world of torsion fields. These are a new and exciting area of modern physics that has the potential to change the way we think about gravity, black holes, and even the Big Bang. Let's begin with the shapes. Einstein's general theory of relativity describes spacetime with a Riemannian manifold, which is a smooth surface that can only be curved. Torsion, on the other hand, can happen in more general geometry models, such as the Einstein-Cartan theory. Imagine that you bend a piece of paper instead of turning it. The curve bends. Torsion has turns. Things are still warped, but not at all the same way. This might sound abstract, but it's a game changer. While curvature is influenced by mass and energy, torsion is influenced by spin, that intrinsic quantum property all elementary particles have. In fact, Einstein-Cartan theory tells us that any particle with spin actually creates torsion in the spacetime around it. That means electrons, quarks, neutrinos, they're not just swimming through spacetime, they're subtly twisting it as they move. Here's where things get really interesting. In Einstein's equations, singularities, those infinitely dense points at the heart of black holes or the beginning of the universe, are unavoidable. The math says everything breaks down. But if you include torsion, that might no longer be the case. At extremely high densities, like those found in the early universe or inside a black hole, torsion could act like a repulsive force, a sort of cosmic counterpressure. Instead of matter collapsing into an infinite point, torsion might stop the collapse, giving us a bounce instead of a bang. This could mean that black holes don't contain singularities at all, but rather swirling quantum cores made of compressed, twisted spacetime. Also, it might help with dark energy, which is one of the biggest problems in physics. Some theories of torsion-based gravity say that a torsion field that is not zero might act like a cosmic constant, moving space outward and speeding up the expansion of the universe. That is, the strange anti-gravity effect we see today might not be a hidden source of energy, but rather a twist in the universe that will never quite get straight again. There's more. Theories like teleparallel gravity don't just twist Einstein's equations, they turn them on their heads. These models only use torsion to describe gravity, Curve is not used at all. It's the same as saying that things fall by rotating them instead of bending them. Some other shapes could help us get to quantum gravity more easily. They could help us combine general relativity and quantum mechanics into a single theory that doesn't have as many problems. But how do we detect torsion? Unlike curvature, which affects all matter equally, torsion might only couple to spinning particles. Its influence would be subtle, delicate, possibly only measurable in extreme environments like near neutron stars, black holes, or during the very first moments after the Big Bang. Some experiments in the 1970s tried to detect torsion by observing how electron spins precess in magnetic fields, hoping to see deviations from what standard physics would predict. No conclusive results were found, but the idea lives on. Today, as we push the limits of gravitational wave detection, probe quantum entanglement at cosmic scales, and build atom-scale gyroscopes for gravitational mapping, there's a renewed push to find evidence for torsion, even if it means combing through the tiny noise left behind after a massive black hole collision. And if torsion is real, it may not just exist passively in the background. It could play a role in phase transitions of the early universe, help explain the matter-antimatter asymmetry, or generate primordial magnetic fields still visible today. Some speculative models even suggest that torsion could help encode information about the universe in a way that's immune to decoherence, something that could link gravity and quantum information in a completely new language. The possible goes into the strange, as with many deep space ideas. Some crazy ideas say that torsion could change memory, how we see time, or even parts of our mind, but none of these ideas are based on evidence. Even so, the real science draws an interesting picture. Torsion could be a hidden force in everything from the rules of motion to the formation of galaxies if space-time can twist, and that twist is connected to the quantum structure of reality. Now, what do we do? That means we might not have the whole picture when it comes to gravity. The information Einstein gave us was a great beginning to the bigger story that the world is telling us. As scientists dig deeper into the Planck scale, where time is recorded in slivers so short they make a yoctosecond look long, they are beginning to see signs of a darker story. It turns out that reality might not be smooth, solid, or even real. Instead, it may be made up of many secret structures, ghost fields, and space that glitches. We've peeled back the universe's surface to see something raw, electric, and maybe forever. If exploring the weirdest corners of the cosmos is your thing, don't stop here. Subscribe to Beyond Horizons, where every video takes you deeper into the unknown.